Podcast is now starting. All attendees are in listen-only mode.
All right, we've got 13 responders to the question here. I'm seeing 95 attendees. All right, so it looks like we have half of our crew, or almost half now, that seem to know enough about noise to be dangerous. So that's good. 20% have little to no working knowledge, so hopefully you guys will learn a lot. And then I could run the show. Awesome, 29% there. Good deal. All right, so we're going to move to the next quick question here, and then we'll go ahead and get started. Oh, awesome. You guys have already answered some. Perfect. So what are you expecting to learn or gain from this course? To be able to answer the public better regarding the PD&E process. Refresher, build upon my knowledge base, do a better job of explaining noise issues to the public. Specifics on FDOT's noise policy and process. Awesome. So a couple of you guys want to address the public better, so that's good. See how it impacts my area of expertise. Latest FDOT noise policies, any updated process information and a refresher, understand design process, have a basic understanding to see how it impacts my area of expertise. Hello, Lisa Stone, hello. Know the correct procedures. Awesome, so we have some good expectations here. Determine noisy areas, gain a basic design knowledge. Awesome. Better understanding of the noise process, learn the basics of FDOT noise process. Awesome. So it looks like we've got everywhere from just general noise knowledge about the, general knowledge about the noise process, and then tending to the public, bettering your ability to do your job and coordinate with others, basic design knowledge. Awesome. All right. So we're going to be using Mentimeter throughout the presentation here. A couple of other administrative items here we've got listed under the handouts tab in the GoToWebinar GUI there. We've got a couple handouts. We've got the agenda, which we're going to go through 4 lessons today, 2 of which we'll be going through the basic PD&E and design noise procedures. Then we'll have a quick break. And then the last two lessons that we'll be doing, we'll be going over the various roles of people involved in the noise process, and then, of course, actually constructing the noise barrier. So my name is Christina Schoonard, and I will be leading the training here. We have Catherine Bradley on the line as well. I believe we have NG Saman and Terry Cook, and then Doug Zhang. So we'll be fielding some questions here and going through all of the training for you guys. We also have, back to the handouts here, we have, so we've got the agenda, and then the handouts PDF has a few resources for you guys to look at. It has the noise abatement criteria and a few other helpful resources. And then the resources page has various noise links that you guys can take home with you to research further into various noise issues and policies, regulations, guidance, etc. So we'll go ahead and get started on the training here. So let's exit out of that and get right on to it. And I've got to bring this guy over here. There we go. Okay, so our first lesson here is the noise study process in the PD&E phase. So in this lesson, the noise study process in the PD&E phase is broken down and important steps are highlighted. We are going to be learning the PD&E process, including the efficient transportation decision making, or ETDM process, identifying PD&E versus design activities, field work, modeling data, which is roadway, infrastructure, traffic, noise sensitive sites, etc., impact determination, barrier analysis, public involvement, construction noise, noise contours, and of course the noise study report. So prior to the PD&E phase, a preliminary review of potential impacts is performed through the Efficient Transportation Decision Making, or ETDM process. This includes a desktop review consisting of a land use review, a review of aerials, a property appraiser website review, and the ETDM process is used for early identification of any potential noise issues and impacts. Note that this process does not actually perform a noise analysis, but rather it is very early on look for any potential issues that may arise. So now we're going to dive down into the actual PD&E process. So after the ETDM process, the PD&E phase is initiated. The PD&E phase fulfills the requirements of 23 CFR 772, which is the Code of Federal Regulations on Noise, and thus NEPA. PD&E studies are conceptual in nature. They may include a screening of multiple viable alternatives, but typically just one is evaluated. During a PD&E phase noise study, the existing roadway using current year conditions, a future no build for design year, and a future build for design year conditions are evaluated for potential noise impacts. Of importance, the PD&E phase noise study does not make any commitments to construct noise barriers. Rather, the PD&E noise study only commits to evaluating any noise abatement further in the design phase. Additionally, a PD&E phase noise study identifies noise contours, which can be used for land use planning purposes. As an important note, that the contours that are developed do not identify impacts. They're very generalized, and we'll get into those a little bit more a little bit later. So just to go over a few regulatory items here, answers to basic questions about the PD&E noise study process can be found in various parts of 23 CFR 772. For example, to find more information about determining the project limits, 23 CFR 772.58 provides helpful guidance. Remember, project limits means the entire specified start and end point of the project. Then information on noise abatement measures can be found in 23 CFR 772.13. Abatement is only considered when found to be feasible and reasonable, which is described later in this training. Primary consideration is given for exterior areas of frequent human use, and of importance, each state highway agency develops their own thresholds for a required noise reduction. So just because we here in Florida have a required noise reduction of 5 decibels to be considered benefited and 7 decibels to meet the noise reduction design goal, does not mean that other states also have that criteria. We have a little bit of leeway with the thresholds that we can pick here. So information on documentation can be found in 23 CFR 772.13G. The Noise Study Report, or NSR, documents the noise evaluation, including the methodology used, the results of the analysis, impacted noise sensitive sites that cannot be provided reasonable feasible noise abatement measures, reasonable and feasible noise abatement measures, and the statement of likelihood, which we'll also go over later in this training. Of importance, FHWA will not approve plans unless reasonable and feasible noise abatement measures have been incorporated if found. Alternative screenings during the PD&E phase can occur. In developing contours, it's important to remember, like I said, that 23 CFR 772 states that noise contour lines may be used for project alternative screening or for land use planning, but shall not be used for determining highway noise impacts, highway traffic noise impacts. The noise contours are typically presented at an alternative public workshop or similar event. The results of the detailed analysis for viable preferred alternatives is typically available by the public hearing. And of importance, the noise analyst needs to make sure that the alternatives are displayed differently from the impacts in a noise study report, as they're not the same. An alternative analysis using contours does not take into account shielding, terrain lines, and more. So when we put together our contours in T&M, our noise model, we do not have any specifics on shielding from buildings or elevations, anything like that. We don't put those into the model. It's a very generalized contour that's developed. It's not specific for any certain part of the project. So that noise contour is only an isopleth, which approximates the sound level at a certain distance from the roadway. A full detailed noise analysis is conducted for the viable preferred alternatives that develops those noise levels a little bit more specifically for each point instead of the contours, and that's how we identify impacts. So let's go over some field work. So field work is performed for 2 purposes during PD&E. The first purpose is to determine existing or ambient traffic noise levels. This happens when you have a new roadway that is coming through, not a widening roadway. And then the second reason is to validate the computer model. So this is essentially where we go out into the field, we take some noise measurements, we observe what's going on in the field, if there's some elevation changes, if there's a ditch like you see in the picture in between your monitor and the roadway. We count the number of vehicles that go by, and then we go back into the office and we build what we've seen in the field. So we enter in all the different traffic data. We set up our quote receptor in the model, which is our noise meter location. So as shown in the picture, if we're about 20 feet or so away from the road or the edge of the roadway, we'll put a receptor in the model to identify what the noise level is at that receptor 20 feet away from the roadway. And we run the model and we compare to see if it is within a certain threshold decibel level from what we actually found in the field. So something that's very important to note here, noise monitoring is not used to determine impacts or abatement reasonableness and feasibility. It is either for determining existing noise levels or to validate the computer model. There's really no other reasons to go out and perform noise monitoring for a typical noise project. So another task that's completed during PD&E is our land use review. This is very important to determine and verify that all noise sensitive sites have been captured properly in the model. New construction or demolition is not always readily discernible in aerial imagery. It could be out of date, or that construction could be happening really pretty recently. The property appraiser's website should be the most up-to-date data source to determine ownership. A field visit can also identify various model inputs such as topography, like berms, ditches, perhaps there's a quick change in elevation that cannot be readily discernible off of Google Earth. Potential shielding, perhaps a warehouse was constructed recently that shields a residence. Ground zones are important, things like water bodies, large concrete areas, etc. You want to make sure that you've identified all of those features to put into the model in order to get the most accurate portrayal of noise levels that you can. All of these various inputs have an influence on what those noise levels will be. For example, if you have a warehouse that was constructed in front of the residence, that would tend to lower that noise level at the residence because you've got a building blocking the noise coming from the roadway. Same thing with ground zones, your water bodies and large concrete areas. That noise is going to bounce off the ground differently if it's grass versus snow versus a water body, large concrete areas, etc. Now, I mentioned snow, but of course here in Florida, we don't have snow very often. But if it were snow, it would definitely muffle that noise coming off of the roadway there. So we want to make sure that we've got all of our ground zones identified properly. So modeling data. Let's talk a little bit about modeling data and what we need in order to produce our model. Many different data sets are needed in order to complete the noise analysis. These data sets include roadway data, roadway elevations, profile, infrastructure, things like bridges, MSC walls, etc., right-of-way, where that line is, stationing, traffic data, both LOSC and AADT, along with your vehicle type percentage breakdowns. We'll get into that a little bit later here in the training. Where your noise sensitive sites are, which, like I've mentioned, those are typically gathered from property appraiser's website and a field visit. Also, if possible, if it's available, sometimes it's not always available at the PD&E phase, pond siting, wet ponds only. We don't want to model any dry ponds because, like I said in the model here, we're identifying where our ground zones are. So if it's not something other than grass or lawn, we want to make sure that we've entered that in. So we don't need to worry about any dry ponds. We only want to worry about wet ponds, or the ponds that are going to be filled most of the year. And then property acquisitions are also helpful. You don't want to model a noise sensitive site if it's not going to be there in the future. Of course, you would want to document the existing levels and the future no build levels for that noise sensitive site. But if it's going to be acquired with the build condition in the future, then we of course don't want to report noise levels at that property that's going to be acquired in the future for the build condition. So roadway data. Roadway data is needed in a microstation or open roads or GIS or Google Earth type of file, some sort of spatial file that the noise analyst can then ingest into the traffic noise model called T&M. The existing, no build, and future design conditions are all evaluated. We take each lane center line and we plot it out and enter it into the model. This includes all of the elevations of each lane and any super elevations. So if the inside lane is perhaps sitting at 23 feet and the outside lane is perhaps sitting at 25 feet, we definitely want to capture that in our model. And then additionally, traffic is entered for each lane. So for each lane, we have points that capture the change in either elevation and or a curve. So for example, if we have a straight long roadway, we could get away with, or a straight long roadway that's very flat, we could get away with not a lot of points placed on our roadway. But if we have a roadway that has changes in elevation that are pretty significant and along a curve, we're going to be placing more points along that roadway to capture the curve and or change in elevation. So you can imagine, especially in an area with like an interchange of several different highways coming together, it can get pretty hairy if you've got a lot of points floating around in space that all have to have elevations, and all roadways need to have traffic entered into them if available. So lots and lots of data that goes into it. So data related to infrastructure should also be obtained. This includes data on roadway elevations, like I said, retaining or mechanically stabilized earth, the MSC walls, super elevations, ITS structures, bridge locations, etc. These items should all be provided to better support the noise analysis. So when it comes to bridges, in our T&M model, we have something that we can check that identifies that the roadway is a bridge and that noise can travel underneath that roadway. So that's one example of why it's so important to identify where bridges are. Mechanically stabilized earth and retaining walls, we need to know that information because we have different barrier height restrictions on those type of surfaces, which we'll get into a little bit later here in the training. Traffic data. So traffic data for non-traffic folks can be pretty intimidating. There's a lot going on. And for us noise folks, we actually have to have a pretty specific traffic data that's entered into our model. So 23 CFR 772 states that in predicting noise levels and assessing noise impacts, traffic characteristics that would yield the worst training noise impact for the design year shall be used. So in the noise world, more cars does not always equate more noise, as congestion can occur, which would slow down vehicles, right? So the more vehicles you have on the road, the slower you're going to go and the less noise that you're going to generate. Therefore, for roadways, the guidance suggests to use level of service C, or LOSC, or demand volumes, whichever is less, except for interchange ramps where demand volumes are always used. And I know that seems a little counterintuitive at first glance, but like I said, the more cars you have, if the roadway can't handle it, then the cars are going to slow down and you're not going to hit that worst noise criteria. So it's very important to receive FDOT approved traffic data developed by a traffic engineer as early as possible, as the noise modeling process takes time. Oftentimes, if anybody here is a noise analyst, you'll probably laugh. Oftentimes we have built our model and we very well might be waiting on traffic data in order to actually hit our run button. So ask for that traffic as soon as possible. For more information, you can see section 1.2 of the Traffic Noise Modeling and Analysis Practitioner's Handbook. It contains some additional guidance on the application of traffic data for noise studies. And that link is actually found in that resources Word document that's found in the handouts tab of the GoToMeeting there. There it goes. So in the PD&E manual, the Traffic Noise Modeling and Analysis Practitioner's Handbook, they provide a flowchart that illustrates the process of either using LOSC or demand traffic volumes. So on the left-hand side there, you can see the path to follow for LOSC volumes. And then on the right-hand side, you can see the path that is followed for demand volumes. So using demand volumes, you have to multiply by a few different other metrics in order to come to the final traffic data that you input into T&M. In T&M, we have to enter the hourly number of automobiles, motorcycles, heavy trucks, etc. for each lane. So in the case of LOSC, we would take that LOSC volume and multiply it by our vehicle type percentages, and then dividing by the number of lanes, because we enter the traffic data in for each lane. Versus demand volumes, we actually have to multiply by the K value in order to determine the hourly, the worst hour, and then the D value, which is the directional factor, to identify the peak traffic on one side of the roadway here. So we've got our peak traffic on one side of the roadway, perhaps going northbound, and then our off-peak traffic on the opposite side of the roadway, perhaps going southbound. So there's a little bit more work that has to happen if we do choose to move forward with demand volumes. But that's all golden because we've got a handy dandy spreadsheet that we use, that we actually fill out the form and it auto computes it for us, and we take those numbers and we just input them right into T&M. And then that spreadsheet is actually captured in our noise study report, where we disclose what the LOSC and or AADT values are and the various metrics that we've applied, the vehicle type percentages, etc. So everything is transparent. So demand values versus LOSC. Demand traffic data is drilled down to peak and off-peak traffic, like I said. When noise-sensitive sites are located on both sides of the roadway, as they often are, the analysts should create two model runs, which represent the worst-case scenario for each side of the roadway. Notably, those receptors should only be found in one of those model runs. So, for example, if we have 15 noise-sensitive sites on the northbound side and 20 noise-sensitive sites on the southbound side, the 15 noise-sensitive sites on the northbound side should only be found on that northbound run where the peak traffic is placed on the northbound lanes, and vice versa. Notably, when we create our model, we often will create a master model. So we've got all of our noise-sensitive sites, all of our roadways, all of our terrain lines and ground zones, and everything that we can possibly fit into the model. And then we'll splice it up and make a copy in order to put peak and off-peak traffic for the northbound, and then peak and off-peak traffic for the southbound. It can get kind of hairy at an intersection where you've got lots of different roadways coming in, and you want to make sure that you've identified the worst noise scenario for each receptor. So like I said, that heaviest traffic would be entered on the side of the roadway closest to the noise-sensitive sites, and then flipped to evaluate the roadway's opposite side. That peak traffic is distributed evenly across all travel lanes, unless there's a known restriction like an HOV or a truck lane. Then the table presented to the right is the example of the FDOT developed LOSC values, which is found in the FDOT Quality Level of Service Handbook. As shown, these traffic values are predetermined based on facility classification type, number of lanes, and a few other factors. So the demand values are much more location specific, project specific, etc. and then LOSC values are more generalized. So I've mentioned vehicle classification before. We have 5 different vehicle types that we are able to enter into our traffic noise model. We have automobiles, medium trucks, heavy trucks, buses, and motorcycles. So automobiles are vehicles with 2 axles and 4 tires. They're your general automobile that you find on the road. Medium trucks are all cargo vehicles with 2 axles and 6 tires. Moving up the line here to heavy trucks, they're all cargo vehicles with 3 or more axles. Buses are all vehicles designed to carry more than 9 passengers. And then, of course, motorcycles are all vehicles with 2 or 3 tires and an open air driver or passenger compartment. So these are pretty standardized, just these 5 different classifications here. And when we go out into the field to count vehicles for model validation, you got to be pretty quick about it. So we'll sit out in the field with our counters, and anytime a heavy truck passes by, we'll press the button for heavy truck, etc. So you got to be pretty quick, especially on those highways with several different lanes. Got to be able to assess the difference between a medium and a heavy truck really pretty quickly there. Automobiles, buses, and motorcycles, those are pretty easy, but it can take some time to discern the difference between medium and heavy trucks when there's a bunch of lanes going on. It's a bit easier when you've got a single 2-lane roadway, but when you've got those larger interstates that you're counting traffic for, it can keep you on your toes. So let's move on to noise sensitive sites. If we didn't have these, then we wouldn't have results in our model, right? So noise sensitive sites are those land uses for which an FHWA noise abatement criteria has been established. So these are identified at the federal level, and a review of the property appraiser's website, like I said, in conjunction with a land use review, so out in the field, should provide sufficient up-to-date information on identifying any noise-sensitive site in the project area. Each noise-sensitive site should be represented in the model. So typically, a single-family residence is represented by a single receptor. However, if the single-family residence has a 2nd or 3rd-story balcony, which I have seen before, an additional receptor can be placed at the balcony to identify the worst noise location of that single-family home. However, of importance when you're counting up the number of noise-sensitive sites, if a single-family home has 2 different receptors representing it, only one noise-sensitive site would be counted, even though there are 2 receptors. Those receptors are just there to identify whichever is worse, that ground floor or the balcony, depending on the location of the noise-sensitive site, because it can vary based on shielding and elevation. And then any non-residential land use, or special land use as we refer to them, may be represented by multiple receptors. So if you have a school with a football field or a place of worship with a playground for the kids, you would want to identify more than one receptor for those special land uses most of the time. Let's discuss some impact determination tasks. So the prediction of traffic noise levels includes the use of FHWA's T&M, or Traffic Noise Model, version 2.5 or newer. Note that the latest version of T&M is actually version 3.0, which came out last year, I believe it was, but there are a few bugs and errors that are being worked out. So we are currently sticking with version 2.5 until the next version comes out. A little bit of inside information, our T&M that we use right now is fairly archaic. It's very basic. It doesn't have the ability to display aerial imagery. It's very basic, a lot of points and lines on a blank white canvas. And the update, the latest version of TNM 3.0, actually incorporates GIS, where you can view an aerial image, which is extremely helpful when building your model. So I'm super excited about that. Whenever they work out those bugs, it'll be a tremendous help to be able to overlay our noise sensitive sites, our points, and our roadways over an aerial imagery in the model. We actually build everything outside of the model on top of aerial imagery so we can see where we're plotting stuff out, and then we ingest those XYs into the model onto a white blank canvas. So I'm very excited for when the next version comes out that enables us to have aerial photography in our model. So like I've mentioned before, typically during PD&E, we evaluate our current year, our existing model. We evaluate the future no build, so the future condition without the proposed roadway. And then of course our future build for our design year conditions as well. All viable alternatives under the study might be evaluated if necessary, but typically, like I've mentioned, only one of those alternatives is typically focused on and evaluated. Once TNM has been compiled, we check for errors. Once it's successfully ran, the noise analyst compares the TNM predicted values to the FHWA noise abatement criteria. So what is an impact? There are two ways that a traffic noise impact can occur. The first criteria for identifying an impact is if the future build, the design year, traffic noise levels approach, meet, or exceed the FHWA noise abatement criteria, or NAC, for a given activity category. I'll show on the next slide here, each of the noise sensitive sites are broken down into a land use type, and each land use type has a different noise level criteria that they are. So you've heard me say the term approach. So an impact is determined if noise levels approach, meet, or exceed the criteria. That term approach is defined by the FDOT as within 1 decibel of the NAC. For example, if the FHWA noise abatement criteria is 67.0 decibels, the FDOT standard for approaching the NAC is considered to be 66.0 decibels. The second criteria for identifying an impact is if the future design year traffic noise levels increase substantially when compared to an existing noise level, which is one reason why we evaluate existing noise levels, so that we can compare to see if noise levels have increased and by how much. So a substantial increase is defined as an increase of 15 decibels or more. And as I've alluded to earlier, each state can choose their different criteria. So just because here in Florida, our substantial increase is defined as an increase of 15 decibels or more, other states may not be 15. They might be 10 or 12 or a different number. So each state can choose their definition of substantial increase there. Same thing for approaching. FDOT has chosen within 1 decibel, but other states very well might choose a different criteria. So here is the FHWA noise abatement criteria. As you can see, there are 7 different activity categories, as we call them: A, B, C, D, E, F, G. Category A is hardly used. In fact, I'm hard pressed to say that we've ever had an activity category A here in Florida identified. These are lands on which serenity and quiet are of extraordinary significance and serve an important public need, where the preservation of those qualities is essential if the area is to complete or to serve its intended purpose. So this is something like the Tomb of the Unknown Soldier, something like that, that is very, very, very important to be serene and quiet. Our second category here is residential, which is what most people think of when we do our noise analysis. We're evaluating for residential areas, your single family homes, your condos, apartments, etc. Your activity category C, active sports areas, amphitheaters, libraries, trails, public meeting rooms, playgrounds, places of worship, etc., parks, medical facilities. A lot of your other your other land uses are considered in this noise sensitive site activity category here. And then likewise for category D, pretty much almost the same types of noise sensitive sites listed here, only this is for the interior locations. So if you see that evaluation location column there, you see exterior, 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 and then we have an interior criteria. So notably in 2010, the federal regs changed where the interior of residences are no longer evaluated. So we do not evaluate the interior noise levels of residences. We only evaluate the exterior. I'll get into more details about that a little bit later, but that's something very important to recognize. And then category E here, we've got the exterior area of hotels, motels, restaurants, pretty much anything that is not included in activity category A through D or F. And then F is agricultural, airports, bus yards, manufacturing, anything that is naturally a louder noise sensitive site, or rather land use, because this category actually does not have an activity criteria. So we do not evaluate noise at manufacturing places or airports. Anything that's listed in this activity category, we actually do not assess noise. We can identify them and say, hey, there's an airport here, there's a mining facility here, etc. But we do not evaluate against a criteria, a decibel criteria, and we do not evaluate noise abatement for those land uses. And then, of course, activity category G, that's any undeveloped lands that are not permitted. This is important to note because if any land is permitted for a specific land use, that's how us noise analysts, we will evaluate that land use. So, for example, if a property parcel has been permitted for a residence and they have a permit for that residence, the building permit to be built, then we will evaluate that parcel as a residential area. Same thing with a place of worship or a hospital. If it's been permitted and they've got a building permit to build whatever that land use is, then that is the land use that we evaluate it for. One other thing that I want to point out here is how much lower the criteria is for interior use areas. And that's because we actually apply a reduction factor. So when we identify noise levels at these places that have an interior noise level criteria, we will actually run that location in the model, and then let's say the model comes back with 75 decibels because they're really pretty close to the roadway there. But we actually subtract 20, 25 decibels or so from that predicted noise level to account for the insertion loss that occurs from the building. And that depends on the building type, whether or not they have single glazed, double glazed windows, etc. And we'll get into that in a little bit more detail later on in this training, but I wanted to point out that that criteria is in fact lower for those interior locations for that reason.
Hey, Christina.
Yeah.
This is Doug. I just wanted to kind of chime in one thing on that, which might be useful for everybody, and that is that we only look at interior use if we don't have an exterior location associated with that land use. So for example, if there was a church and there was an exterior use at that church, we would treat it as activity category C and assess the exterior use. We wouldn't look at activity category D. Activity category D is only for those land uses where there is no place of human usage outside.
Yes, yes, that is an excellent point, Doug. Thank you for bringing that up. And that goes as well for residential areas, actually, which is a bit surprising to hear and can cause some public uproar in certain occasions. For residences, like I mentioned in 2010, the regulations, the federal regulations changed so that we don't look at interior noise levels of residential areas. For single family homes and most duplexes, et cetera, it's not really a concern because they have a front yard or a backyard that they can utilize, which we consider an exterior area of, quote, frequent human use. But if it is for example, like a condo or an apartment complex that each individual unit does not have a balcony, and let's just say that that condo or apartment complex does not have a community pool or a barbecue area or you know, a little playground or park or anything like that. Let's just say that it is, you know, shoved in this really high dense urban area where they just don't have an outside area of use and no balconies or anything. That residential area would actually not be evaluated because there's no exterior use area. So like I said, that can cause some public outcry, especially if the PD&E was completed prior to the regs changing in 2010. You know, if they were previously evaluated because they have an interior criteria and now they don't. I have seen projects have quite some uproar when that changes. So thank you for bringing that up, Doug. Yeah, exactly. We do not evaluate interior if an exterior area has been identified. So going back to perhaps a place of worship, some places of worship have playgrounds for the kids and others do not. So 50-50 chance oftentimes I've seen where a place of worship will be evaluated as exterior, or if they don't have a playground, then they will certainly be evaluated as interior. Thank you, Doug. All right, moving on to our next slide here. So like I said, to be considered impacted, I just want to stress this again, for the future build design year. So we don't identify impacts for existing conditions. The impacts are identified only for future design years. If the noise sensitive site approaches, meets, or exceeds the NAC within 1 decibel, which is what we just saw on the last slide there, or if they increase substantially from existing levels of 15 decibels or greater. So T&M predicts sound levels to the 1/10 of a decibel. There is no rounding that we consider here in Florida. For example, a residence, their criteria is 66.0 for approaching. I'll back up to this slide so you guys can see this again. We have our I'm trying to highlight the, take my pen here. Let me see if I can do a laser pointer here. There we go. So we've got our activity category B for residential areas. We have our FHWA criteria of 67, but in order to approach that criteria within 1 decibel, FDOT approach within 1 decibel, our criteria for residences is 66.0. So for a residence, 65.9 is not considered impacted, but 66.0 is considered impacted because there's no rounding. So likewise, an increase of 14.9 decibels compared to existing conditions is not considered substantial versus 15.0 is considered substantial. All right, so we've got a live poll break. Everybody get excited because we're having some friendly competition here. So let me get this all pulled up. We want to bring up menti.com if you guys want to go there. And we're going to bring over our presentation onto this screen here. Oop, uh-oh, we don't want to show the answers quite yet. All right, lesson 1, question 1.
Christina, what is the code we enter if we want to enter the poll?
It is 2741-7951. I'm resetting the results here. For some reason, it's not resetting. Bear with me for a second. I'm not sure why it's resetting here. Maybe it, okay. All right, let's see here. All right, we've got quite the number of people here. 31. All right, press enter to start a countdown. All right, is everybody ready? You got to answer fast to get more points. The NAC category for a cemetery is, we've got 20 seconds to answer. All right, time's up. Let's see what everybody picked. All right, good job. It is indeed C. All right, next question. NAC activity category for a place of worship with no outside use. Awesome, it is D. So it does not have any outside use. So we would go with that interior criteria for category D. A high school football field. C, correct. Nice job. A duplex, single-story residences. Very nice. B, that's right, residences. All right, I think this is our last question. A storage warehouse. Very nice, guys. Great job. All right, let's see who won. Woo, we got some competition, guys. Woo, nice job. So we'll be doing these throughout the training here. if you would like, keep track of how many points you made during each session here, and we'll add them all up at the end and see who our final winner is. Mentimeter doesn't have the ability to concatenate all these challenges here, so if you would like to know who the overall winner is, keep track of your points and we'll announce a final winner at the end, if you will. All right, we'll close out of that. Keep that window handy though, because we will be doing a few other polls, like I said. So I think there should be a button available that says join another survey or join another quiz competition. Go ahead and click that, and then you'll have it ready for our next poll that will enter in the number there. All right, so let's get into some more details for modeling. We have our barrier analysis. So 23 CFR 772 requires that where impacts are identified, at a minimum, abatement in the form of a noise barrier should be considered. Other forms of abatement may also be considered, such as traffic management, alternative roadway alignments, property acquisition for buffer zones, insulation of activity category D land uses, etc. Of note, the construction of noise barriers includes the acquisition of property rights, either within or outside of the right-of-way. Furthermore, landscaping is not considered a viable abatement measure. So traffic management oftentimes is not a viable option for noise abatement. Oftentimes the point of a new project is expanding a roadway and more traffic, putting more traffic on that roadway. So it would kind of defeat the purpose there. You can also limit trucks as a form of traffic management, but oftentimes, excuse me, oftentimes these roadways are a transportation network for shipping, and limiting trucks would likely not be a good thing to do. Alternative roadway alignments, oftentimes other more significant features or resources will drive where the roadway goes if it's a new alignment. If it's a current alignment, shifting that roadway alignment might be a little bit more difficult if the roadway is already there. So that oftentimes is not a viable abatement measure. Property acquisition for buffer zones. This could happen, but it oftentimes is not a viable abatement measure because the property has already been established, et cetera. It'd be much more expensive to buy those properties than to go ahead and build them a barrier. And of course, upsetting the public if you're going to buy their property instead of building a barrier, that's not exactly the best thing to do. And then installation of activity category D uses such as recording studios, places of worship, schools, etc. Oftentimes that's not what is pursued, rather a barrier is pursued. And on that note, it is quite actually rare for an interior land use to be impacted because of that, the reduction that occurs from being inside. That 20-25 decibel insertion loss that we tack on to the predicted noise level oftentimes brings that noise level below the criteria here for activity category D for 52. It would have to be pretty loud outside in order for that interior to be impacted. All right, so let's go over some feasibility and reasonableness requirements for barriers. Abatement measures have to be both feasible and reasonable to be considered. So definitions of feasibility, that is the combination of acoustical and engineering factors that are considered in the evaluation of a noise abatement measure. There's some details there in 23 CFR. And then reasonableness factors include a combination of social, economic, environmental factors that are considered. And again, 23 CFR has more details. So for feasibility, noise reduction requirements. This is for both PD&E and design. Here in Florida, we have to receive at least a 5 decibel reduction, or that is called a benefit in the noise world, at a minimum of 2 impacted receptors. So a receptor is a representative location of a noise-sensitive site or area for any of the land use categories that is listed in FHWA's noise abatement criteria table that we looked at earlier. Engineering considerations are also a feasibility factor, but this is done during design only, which we'll get into a little bit more in detail in some of the other lessons here. Can the noise barrier be constructed as designed? Are there safety issues or drainage issues, right-of-way, access requirements, utilities and maintenance that can be a factor that can prevent a noise barrier from being built? So we have to look at all of these factors to make sure that the noise barrier can actually be built. Does it serve an acoustic purpose? And can it be built? Reasonableness, so the other side of the coin here. We have to consider the viewpoints of benefited, which is those properties that are getting a 5 decibel reduction because of the barrier. So we have to consider the viewpoints of the benefited property owners and residences. But again, this is completed during design. We also have cost effectiveness criteria. We estimate our barrier total cost at $30 per square foot. And yes, this is revisited every few years. We make sure that that's $30 per square foot is still accurate based on inflation and cost of materials, etc. And then we also have a $42,000 per benefited receptor for both PD&E and design phases. If a barrier exceeds that $42,000 per benefited receptor, it is considered not cost effective. And then we have our noise reduction design goal. At least one benefited receptor must achieve a 7 decibel reduction for both PD&E and design phases. All of the above factors must be achieved at each noise barrier system to meet reasonableness requirements. If any of these factors are not met, then the barrier is not carried forward and not suggested into the design phase or to be constructed. So for an example for cost, like I said, that cost effectiveness criteria is $42,000 per benefited receptor. If a barrier costs an estimated $420,000 for total cost of construction, then at least 10 receptors or residences must benefit from the barrier in order to be cost reasonable. So that's 420,000 divided by 10. You've got your 42,000 per benefited receptor limit. Otherwise, the noise barrier would not be considered cost reasonable, and we would not pursue that. We would, of course, document all of this in the noise study report so that everybody can see, yes, we did look at a barrier, and at each of these heights, it was not considered to be cost reasonable. So, for example, if we had 9 benefits instead of the 10, then it would come out to 46,000, and it would be above that 42,000 per benefited receptor, and we would not pursue the barrier further because it's not cost reasonable. So feasibility and reasonableness during PD&E more. Only cost and noise reduction requirements are considered during PD&E. Like I mentioned earlier, that looking at the engineering side of things is done more during the design phase. So in order for that noise barrier to advance to be considered during design, that noise barrier must, number 1, achieve the noise reduction design goal, which is the 7 decibel reduction. Number 2, it must provide a 5 decibel reduction to 2 impacted receptors. And number 3, the noise barrier must cost $42,000 per benefited receptor or less. Failure to achieve any of these is known as a fatal flaw, and that barrier would not be pursued further. Other considerations can be noted, but further evaluation would occur during the design phase. So for non-residential land uses, or quote, special land uses, the special land use methodology is applied to evaluate noise abatement. So this is applied to activity categories C, D, and E. And of course, A, if we had one here in Florida, but like I've hinted at earlier, there aren't any activity category A's here in Florida that I'm aware of. So the methodology is applied to these areas of impact rather than a discrete location such as a residence. So a residence has a single receptor placed at typically the corner of the dwelling unit, versus special land uses, you might have several different receptors. So I've mentioned the school with the football field earlier. Perhaps you've got a football field and maybe you've got a track and a playground and maybe a basketball court as well. You would place receptors at each of those frequent human use areas of outdoor use in order to determine whether or not any portion of that special land use is impacted. If it is impacted, you would go through the task of creating a grid of receptors to determine just how far the extent of the impact is. And then you would also use that same grid to identify how much of that property is benefited. So in order to evaluate the amount of impacted area that might be benefited and the amount of time people might spend in the impacted area and benefited area, that actually translates into a cost per person hour per square foot of barrier. So I know that's a little bit difficult to digest, but there is a formula that we actually use to calculate whether or not there is enough people that use that special land use in order to justify the cost of the barrier. And just as a side note here, the special land use methodology was developed in 2009. And as I've mentioned previously, the FHWA noise abatement criteria and 23 CFR was actually amended in 2010, just after this special land use methodology was released. And as a result, the special land use methodology doesn't line up exactly with the current 23 CFR noise activity criteria. So we are actually in the process of revamping the special land use methodology for that reason, and to be able to combine analyses between residential and special land use noise sensitive sites. So as our current methodology stands right now, we evaluate residences and special land uses separately. There is not really an easy way to combine an analysis if perhaps a school or a place of worship is located right next to a residence, and that school or place of worship is impacted. We do a separate analysis for that special land use versus combining an analysis, a barrier analysis for both the special land use and the residential area. So I'm very excited for when that methodology comes out, because we can evaluate a barrier for a continuous noise sensitive site area versus segregating the non-residential and residential analyses. Sometimes that would end up with the barrier being reasonable, sometimes not reasonable, just depends on location. So here's an inside peek into that formula that I mentioned for the special land use methodology. We have an abatement cost factor. It's $42,000 per residence. We have 2.46 people in each residence. We assume that the usage for each residence is 24 hours. And then we have a standard 14-foot times 100-foot for our barriers. And it comes out to $995,935 per person hour per square foot. So the abatement cost is considered reasonable if the calculated abatement cost factor is below the criteria of 995,935 person hours per square foot. So these metrics were considered after careful examination of typical noise abatement provided in Florida. Again, this was back in 2009, so those criteria have likely changed since then. Another reason why we're revamping our special land use methodology now. Noise abatement costs, like I said, is considered reasonable if that is below the $995,000 limit. And for more detailed information, you can consult the FDOT's guidance document titled A Method to Determine Reasonableness and Feasibility of Noise Abatement at Special Land Use Locations. That is also found in the list of resources Word document in the handouts tab of the GoToMeeting here. So what if we don't exactly know the usage of a special land use? Oftentimes we are tasked with contacting the special land use to get an idea of what their usage is. And sometimes that special land use may or may not get back with us, or they might not know their true usage. So this is a spreadsheet that we use not only to calculate the if a barrier is reasonable and feasible, but we can also use this spreadsheet to, in a way, back into our answer. So we will plug in all of our criteria, such as the length of the proposed barrier, the height of the proposed barrier. We can assume that the average amount of time in hours per person that visits is maybe 1 hour. And then we can play with the number here in order to figure out if the abatement is reasonable or not. What the spreadsheet will do is it'll take all the criteria that has been entered in, or sorry, all the inputs that have been entered in, and then match it up with the criteria, and we have a nice handy dandy result here based on the usage that is plugged in. So once we plug in all of our inputs on line item 1, 2, and 4 here, then with line item 5, we can play around with the number to make it reasonable or not, and we can identify what the minimum usage has to be at that land use, that particular land use. So for example, if we have a really small place of worship that might only have 10 parking spots at the facility, and we find out that the minimum number of people that have to use this place of worship is maybe 3,000 people. That's going to be a pretty obvious indication that a small place of worship with only 10 parking spots and no additional parking around it, they probably won't hit that 3,000 person hours requirement in order to make that barrier be cost reasonable. It's best to be able to contact the special land use in order to actually obtain their feedback. That can be documented. If it's a phone call, it can be, you can document their answer in a memo that documents the phone call. If it's an email, that's even better because you have written documentation. But we do try and document whatever that response is from the special land use in order to provide proof that this is what their usage is, if they were aware of what their usage was. There we go. All right. So like I mentioned earlier, FDOT does not commit to noise barrier construction during PD&E. Let me say that again. They do not commit to any noise barrier construction during PD&E. We commit to detailed reevaluation of PD&E identified potentially feasible and reasonable noise barriers during the design phase. So like I've mentioned earlier, PD&E is quite conceptual in nature. Imperative details might be unknown at the PD&E phase. During the PD&E phase, noise barriers are committed to a more detailed evaluation during the design phase, and a statement of likelihood is included in the PD&E phase noise study. So this statement of likelihood is based on the feasibility and reasonableness analysis completed at the time of the environmental document is being approved. So that statement of likelihood essentially states that FDOT is committed to building barriers so long as during the design phase they still proved to be reasonable and feasible. They have gone through an engineering review, which states that there's no safety or maintenance, right-of-way issues. All that jazz has been taken care of, and the barrier can be built. And like I said, they check off the boxes of reasonable and feasibleness for the barrier based on a more detailed evaluation of that design. So let's talk a little bit about public involvement during the PD&E phase. It's a little bit less involved during the PD&E than design, but there's still a lot of things that happen for public involvement during the PD&E phase. So during the PD&E phase, public involvement typically consists of one workshop and perhaps even a public hearing. The alternative workshop seeks public input on proposed alternatives, and a detailed noise analysis and abatement evaluation is not made available at that point in the process. It can be stated that a noise analysis is simply underway at that point in time. During the PD&E public workshop, a qualitative assessment of noise can be discussed in broad terms based on public controversy, but impacts are not generally identified to avoid public assumptions about noise barriers. So the last thing you want to go to the public during PD&E is, oh yes, we see that you're going to be impacted. We're looking to put a noise barrier in, and then the public will take that and go, oh, I'm getting a noise barrier. And then they'll be pretty disgruntled later on if that barrier does not work out to be reasonable and feasible or has some engineering constraints, etc. So sometimes those PD&E public workshops are held before the noise analysis is completed. And during the public hearing, which is a little bit later in the PD&E process, the results of the detailed analysis, abatement measures that are recommended for further consideration during the design phase, and a draft of the noise study report can be provided. During the public hearing, a detailed noise analysis has typically been completed, and a draft noise study report will be made available, like I mentioned. The locations of potentially feasible and reasonable abatement is also provided. So oftentimes there'll be maps depicting controversial areas and what the preliminary results of the noise study report found. Stressing the word draft there. Importantly, the noise study report is not finalized until after all public involvement is complete. We typically document public comments related to traffic noise. This can be incorporated into the public involvement section of our noise study report. And then copies of the written comments can be included as an appendix if desired. So the district noise specialist actually keeps track of any public comments or complaints so that public involvement may be focused on specific problem areas. And like I mentioned, that NSR is not finalized until all public involvement is complete. So construction noise. This is actually pretty simple and straightforward. Here in Florida, we have a standard statement that is inserted into our reports. We identify sites that might be potentially impacted, such as residences, schools, TV, radio facilities, etc. We simply document in the noise study report an environmental document for the project, and abatement in the form of noise barriers is not provided for construction noise because construction noise is temporary. We, like I said, typically just have a standard statement that is inserted into this section of the noise study report. And then figure 18-9 from the PD&E, from FDOT PD&E manual, identifies various noise sensitive sites that are, or rather sites that are sensitive to both construction noise and vibration. So you see those sites listed here. But again, just a standard statement is inserted into the noise study report. So noise contours, I mentioned these at the beginning of our lesson here. To provide a little bit more details, the PD&E phase noise study report should include noise contours. The contours provide an estimation of the distance to impact criteria for each noise abatement criteria. So after location and design concept acceptance, or LDCA, otherwise known as the approval of the environmental document. Noise contour information should be provided to local government officials for land use planning purposes. So as a reminder, these noise contours do not identify impacts, but rather they are a generalized isoplyth that can identify approximately where those decibel levels are out from how far out they are from the roadway here. So to give you an example of what noise contours look like, this is actually a screenshot of TNM, our noise model. Traffic noise model is what it's called. And as you see, like I mentioned earlier, it's pretty basic. We've got a white canvas. We don't have an aerial imagery. We've got our points, which represent receptors. And then those lines at the bottom of the screen that you see are actually our roadways. So we plot in our center lines of each lane. We plot in our shoulders. This is a nice and easy example for our contours here. We typically have just straight roadways going through. We'll enter in our generalized traffic. So there's no curves, there's no elevations, there's no structures that are blocking in between the roadway and the receptor. And then we place our 3 dots, one to represent 56, one to represent 66, and one to represent 71. And we run the model, and then when the model tells us, oh, it's at 67 decibels, then that's our hint to, okay, we need to move that receptor a little bit further away from the roadway to get it down to 66 decibels. So we play with where those receptors are in the model in order to find out how far away that particular receptor needs to be in order to identify 56.0, 66.0, and 71.0. So as you can see, the quieter it gets, the further away from that roadway you get. And then when it comes time for the report, we have this handy dandy graphic that we put together that shows each of the noise abatement criteria activity levels and the distance estimated from the edge of pavement that it would be. So if you note, there is no activity category D. We don't do contours for activity category D. One reason is because of the various insertion loss that happens for that activity category criteria. And then furthermore, that criteria is in fact lower than your 56. So it would be even further out than that, that activity category A there. So finally, let's talk about the noise study report. So the noise study report, or NSR, should detail the methodology and results from the highway traffic noise analysis. The NSR should contain the methodology, the results of the traffic noise analysis, including a table of noise level results and aerials depicting the noise sensitive sites. It should also have conclusions, contain the statement of likelihood that we've mentioned earlier, not a commitment to build barriers, stressing that again. It addresses construction and vibration, any community coordination, and the FDOT PD&E manual, chapter 18 on noise, actually provides a handy dandy example outline to follow for both the PD&E noise study report and the design level noise study report addendum. They do vary slightly with what they report, and we'll get into that a little bit later in the next chapter here. So the NSR should obviously also document potentially reasonable and feasible noise barriers. However, the PD&E level NSR should not commit to any noise barriers, stressing that again. It should be a hint for the exam question later, haha. Instead, that statement of likelihood should be included that states potentially reasonable and feasible noise barriers will be reevaluated further during the design phase. All right, we've got another quick poll here. So lesson 1, question 2. So let's go to menti.com again, and you're going to enter in the code 76190615. All sorts of little avatars showing up. All right. Oops, still a few more people. Okay. So let's go ahead and get started here. All right, remember, answer fast to get more points. Methodology that is used for non-residential land uses is referred to as special land use methodology. Good job, guys. All right, question 2. FDOT must provide noise barriers for construction noise. True or false? False. No noise barriers for construction noise. Good job. Question 3. At minimum, according to 23 CFR, abatement must be considered in the form of noise barriers. Nice job. So all of these other abatement measures, they can be considered, but 23 CFR 772 says at minimum, noise barriers at minimum must be considered. All right, 4th question. Noise contours can be used for determining impacts. True or false? Oh, close call on this one, huh? So noise contours are the isoplus that are very, very generalized, that are used for noise planning, for land use planning. Noise contours do not identify impacts because they're very, very generalized. We don't input things like buildings and shieldings, and we don't get into the nitty-gritty of elevation. It's very, very, very generalized. So noise contours do not determine impacts. We identify impacts from the actual receptors that we input into our model. That is a nice, specific, detailed model that includes shielding and ground zones, any elevations and terrain lines and berms and things like that. So noise contours do not identify impacts. So that is false. All right, last question. FDOT commits to noise barriers during the PD&E phase. Hopefully everybody gets this one right. All right, false. FDOT does not commit to noise barriers during the PD&E phase. We have a statement of likelihood that goes into our noise study report. After we have identified which barriers could be potentially reasonable and feasible, we state in our PD&E phase noise study report the statement of likelihood, which says these barriers work, but we'll build them only if in the design phase, when we have a more detailed look at what's going on for the project, if these barriers will actually work. And remember that engineering review only happens in the design phase. So when we're in the PD&E phase, if we were to go to the public saying, oh yes, you'll get a barrier, and then we haven't completed that engineering review to make sure that there's no safety or maintenance, right-of-way, utility, etc. conflicts, then the members of the public would be pretty upset to find out that we can't build the barrier because, well, we can't actually build it because of whatever safety, etc. reasons. So let's see how everybody did. Wow, pretty close, guys. Nice job. All right. Nice job, Frosty. All right, like I said, if you want to keep track of your overall score there that you got, we'll add them all up at the end, and we'll see who wins. So this concludes our first lesson here. If anybody has any questions, feel free to speak up now, or you can send an email to oem@dot.state.fl.us. I'm actually not quite sure if participants have the ability to speak up, but if you want to answer or type your question in the little chat window box, we'll be sure to pay attention to that and answer your questions as we can. We're going to leave this first presentation here, and we're going to go to our second one. So do you guys want to take a quick break right here? I know we were scheduled for a break after the second meeting, or second lesson, but perhaps we can take a quick 5-minute break now. We're running a little bit behind, but I think we can make up that time in some of the other lessons. So let's go ahead and take a quick 5-minute break. We'll return here. It's 9:39 right now, so we'll return at 9:45. How does that sound? I think I can put a timer up here on the screen that'll help everybody. All right, we'll be back in 5 minutes. All right, our 5-minute break is up, and we're going to be going right into the second lesson here, the noise study process in the design phase. So the design phase, we're going to talk about the differences in the design phase compared to the PD&E phase, design phase specific activities, the noise barrier analysis in the design phase, more information about the engineering review that happens in the design phase. Of course, the noise study report addendum, which is the design phase noise study report, and then public involvement. So we're going to take a look at differences between PD&E versus design. So like we went over last lesson, the PD&Es fulfill requirements of 23 CFR. They're conceptual in nature and include a screening of perhaps multiple alternatives, but typically just that preferred alternative is done. During a PD&E phase noise study, the existing roadway, a future no build, and future build condition are all evaluated. So there are 3 different scenarios. Like I stressed last lesson, the PD&E phase study does not make any commitments to construct noise barriers. They commit to evaluating noise abatement further during the design phase. And the PD&E phase noise study identifies noise contours, which can be used for land use planning purposes, not impact determination. So design phase noise studies. A noise analysis reevaluates the commitments made during the PD&E phase based on the current roadway design being evaluated. So note that the design may or may not have changed since the PD&E study was completed. In the design phase, the existing and no build scenarios are not evaluated, only the future build condition is evaluated. So substantial increases are typically identified in the PD&E phase, not the design phase. Notably, if substantial increases are not identified during the PD&E phase, we definitely do not reevaluate existing and no build scenarios. However, if substantial increases are identified in the PD&E phase, you may or may not have to reevaluate existing conditions to reestablish if a substantial increase is in fact occurring based on the latest and greatest design. So that's not always a hard rule that existing and no build scenarios are not evaluated during design, but during the typical project, which most projects do not identify substantial increases because most projects are widening and not new alignments. Typically, we do not evaluate existing conditions during design because substantial increases have not been typically identified. So the design phase noise study utilizes much more detailed data than what was used during PD&E phase, and the design phase noise study does make final commitments to construct those noise barriers, but only after an engineering review and public input is solicited. So like I mentioned, the last thing you want to do is go to the public and say, hey, we've got this great noise barrier for you because we think you're going to be impacted in the future. And then maybe the engineering review comes back and it can't be built. Or maybe you go through the engineering review and it's good to go and everything works out and you build the barrier and then the public goes, wait a second, we didn't want this because it makes us feel confined, or it's blocking the sunlight from our community garden, or we like the view of the highway, we like the noise because it puts us to sleep, whatever their reason is. Sometimes the public really just doesn't want a barrier. So you want to make sure that the public does in fact want what you're building, especially if it costs a lot of money. So this is a handy dandy table of some of the differences that can be highlighted for a typical PD&E phase study for noise versus a design noise analysis. So of course, that first slide item there, review the PD&E study. Of course, you can't do that in PD&E if it hasn't been completed yet. So that is an activity that is only done during design. Modeling that existing roadway and no build condition for the future. That's something that is typically only done during PD&E. Modeling the future build condition. We do that, of course, for both PD&E phase and design phase. Taking ambient measurements. So this is some of the field work that is done to establish existing conditions. Remember, there are two reasons why we go out into the field. One is to take ambient measurements. There are two reasons we take measurements in the field, rather. One is to take ambient measurements to establish existing conditions. And the other reason that we might take measurements in the field is to validate the model, to essentially tell the public the model is indeed working how it should work and it's predicting accurate noise levels for this area. Those two tasks of taking measurements in the field are typically only done during PD&E. Of course, the ambient measurements to establish existing conditions. If substantial increases are not identified, then there's no reason to retake ambient measurements during the design phase. Same thing with validation. If the T&M model is the same model that was used during the PD&E phase, that validation does not have to occur during design again. However, if, let's just say, T&M version 1.0 was used during the PD&E phase, and now here we have T&M 2.5 that we're currently using, that validation would need to be done again because there's been several updates to T&M since those various versions that influence those noise levels. Same thing with a different noise model. The previous model to T&M is called Stamina, and there are plenty of PD&E studies that use Stamina that have yet to go into the design phase or are currently in the design phase, and those projects also need to have model validation completed again. So again, this is just for a typical project. Normally, if a PD&E project was done with T&M 2.5, you would not have to revalidate the model in design. Next line item here, identifying impacts. Of course, you want to identify impacts both during the PD&E and the design phase. Since that PD&E phase is pretty conceptual, design has more detail, so you want to make sure that you're identifying impacts in both phases. Same thing with your barrier analysis and optimization. You've got your preliminary ideas of where barriers will and will not work during PD&E, and you solidify those barriers during the design phase. And then the engineering review, like I've mentioned, that does not typically happen during PD&E phase because PD&E is pretty conceptual. You want to make sure that you complete that engineering review after you've got all those nitty-gritty details, all your super elevations, all of your exact XYs, where that roadway is going to be, etc. You want to complete that analysis during the design phase in order to pass that information to the engineers for their engineering review. We'll get into much of the nitty-gritty later on. And then community coordination. This is specifically talking about surveys, not necessarily public involvement for meetings and hearings and such. Community coordination in the form of surveys that is typically only done during the design phase. Again, after that engineering review is done, because you don't want to go to the public saying, hey, here, do you want this barrier? It would work great, and not know if it can actually be built or not. And then finally, that last line item there, committing to noise barriers. So we don't commit to noise barriers during the PD&E phase. We only commit to them during the design phase after that engineering review, community coordination, etc. After all that has been completed and we've checked all of our boxes to make sure that the barrier works acoustically, it's cost reasonable, it meets all the engineering requirements, and the people want it, then we can commit to that noise barrier and we can document that in the noise study report addendum. So more detailed look into the design phase activities here. So during design, a number of steps are taken in order to reevaluate a noise barrier. That first step, like I've mentioned, is to review the PD&E phase noise study report. We've of course got a land use and field review, possible model validation, like I've mentioned, if the model has changed. Oftentimes we'll also still revisit the field because typically there's been enough of a lapse in between PD&E and design where land use has changed. So not only will we look at property appraiser website again, but we will also actually go into the field to make sure that property appraiser is reflecting the most up to date, etc. So we do take a second field trip out to the field in the design phase as well. Like I mentioned before, that active building permit is really, really important. If a residential neighborhood is has been cleared but not permitted, we do not evaluate noise for those residences if they do not have a building permit. So that is the key there. In order to be considered for noise abatement, you gotta have a building permit. We also review current federal, state laws and regulations, may or may not have an impact on the project. Like I said, the 23 CFR, the federal regulations for noise changed in 2010, so you may or may not have a change in regulations when going from PD&E to design, depending on when your PD&E study was completed. And then, of course, you reevaluate barriers previously identified as potentially reasonable and feasible. If no design changes have occurred since PD&E, you typically only evaluate previously identified potentially reasonable and feasible noise barriers. And then on the opposite spectrum, if design changes have indeed occurred, which is most of the time I've found in my experience, you reevaluate pretty much the entire project limits for noise abatement. And then changes to design changes are identified by the type 1 project matrix found in the FDOT PD&E manual. I believe it's one of the last pages there in the manual. So things like adding a lane or volumes changing, anything like that. If you move the roadway alignment horizontally or vertically by a specific amount, then that counts as a design change. So there's a whole matrix that lists various examples of changes that would qualify for a noise analysis. So, as previously mentioned several times, commitments to construct noise barriers are not made during the PD&E phase. Instead, they are made during the design process, that design phase. This is because the PD&E phase is conceptual in nature, very generalized. The design level analysis should include design level detail based on proposed roadway design and survey information, etc. Additionally, the only alternative that is evaluated is the preferred alternative, and only for the future build condition. The existing and future no build conditions are not typically evaluated during design. During design, you only evaluate that proposed roadway design. There is no evaluation of existing or future no build. There should only be one roadway design that is being evaluated, not multiple alternatives. And then finally, you make commitments to construct those noise barriers in the design phase. So addressing changes. Like I mentioned, there's that type 1 matrix that is in the PD&E manual, FDOT's PD&E manual. So if changes are identified in the design, we evaluate whether those changes are large enough to warrant a reevaluation of noise. These changes can include significant horizontal or vertical alteration, additional capacity, or other improvements not evaluated during PD&E. Note that small changes, roadway alignment shift of 1 to 2 feet or so, may not require a reevaluation of noise. It's important to consult the district noise specialist to verify anytime there is some sort of change. So if changes have occurred, then traffic noise will be reevaluated. If no abatement was found to be reasonable and feasible during PD&E and the design has not changed since PD&E, no modeling would be performed. And again, that level of documentation is at the discretion of the district noise specialist. If changes from the original PD&E are identified, a reevaluation of noise of the entire project corridor may be warranted. As previously mentioned, this would typically only involve reevaluating for the design year build condition only. Importantly, the traffic data used in the PD&E study should be checked to make sure if the data is still current or if it needs to be updated. Oftentimes, traffic data changes throughout the lifetime of a project, and this can have a large influence on the outcome of the noise levels calculated. So make sure that that traffic is up to date and make changes if necessary in your model. So just another note about substantial increases. If substantial increases were identified during PD&E, you need to coordinate with the district noise specialist to see how the district wants to handle that substantial increase. Typically, that would involve reevaluating the existing condition to re-ascertain if substantial increases are indeed still happening, or if perhaps the corridor has been shifted away from the noise sensitive sites, that they no longer have a substantial increase, which I actually have seen that happen before in between PD&E and design. So during the design phase, barriers which were identified as potentially reasonable and feasible forms of noise abatement are reevaluated to determine if they still meet the requirements. Again, because PD&E is conceptual and design is more detailed, we want to make sure that those barriers still work. If noise barriers are still found to be reasonable and feasible forms of noise abatement, the barrier is put through an engineering feasibility review. Once the engineering feasibility review is complete, if the barrier can be constructed, then we proceed with public involvement. The future design year build conditions are reevaluated and noise impacts are reassessed. Importantly, this engineering feasibility review is performed before any commitment to the public is made about providing noise abatement. I want to stress that. So engineering review has to happen before any commitment to the public is made. Because the last thing you want to do is say, hey, member of the public, you're getting a barrier. And that engineering or feasibility review comes back and says that the barrier cannot be constructed. All right, we've got another poll break for this lesson. So lesson 2, question 1. All right, so we're going to go here. Back to Mentimeter, and we've got code 16687474. All right, let's begin. Remember, answer fast. When is the following activity performed? An engineering review. Whew, you guys are answering fast on this one. All right, design. So we don't take that barrier for an engineering review until the design, because we need more details than what the PD&E phase can provide us. All right, next question. When is the following activity performed? Commitment to build a noise barrier. You guys have a second chance on this one. During design. Very nice, guys. All right, question 3. When is the following activity performed? Modeling existing and future no-build conditions. Again, in a typical project. Very good. During PD&E. So during a typical design project, we don't bother with modeling existing and future no-build conditions if there has not been a substantial increase identified. All right, next one. When is the following activity performed? Ambient measurements. So again, ambient measurements are going out to the field to establish those existing conditions to get an idea what the noise levels are in the project area. Very nice. Yep, PD&E. So we typically only look at existing conditions during PD&E. So that's what ambient measurements are used to establish, is those existing conditions, particularly when a roadway is a new roadway that's going to be built. We want to make sure what the noise levels are, because our model can't predict noise levels if there's no current roadway there. So we go and take ambient measurements to establish those existing conditions. All right, last question, guys. When is the following activity performed? Community noise barrier surveys. So asking the public, do they want the barrier that we've found to be reasonable and feasible? During design, very right. Yep. So we do not want to go to the public and ask them if they want a barrier until the design phase. Once we have solidified that a barrier is reasonable and feasible, it's gone through an engineering review, all the safety, maintenance, right-of-way, utility, etc., all those problems have been solved. Then we go to the public and say, hey, do you want this barrier? Because you might be a little noisy in our future condition. So that happens during design. All right, let's see who's our we're on our leaderboard here. Nice. Awesome. Very nice job, Lola. All right. So moving right along. Good job, guys. Let's take a closer look at the design phase noise barrier analysis. It's very similar to our PD&E phase, so I won't spend too much time on this. Phase 3 plans, or 60% plans, are ideal. Modeling typically begins with 30% plan phase 1 plans, since this is when a firm line and grade is established and roadway cross sections are ready. But in the design phase, it's typically more like 60%. So remember to review subsequent plan sets for changes if subsequent plan sets have been used during PD&E. Roadway elevations can be obtained from cross sections or profiles. Sometimes LiDAR data may be appropriate to use. Bottom or ground elevations for elevated noise barriers are often obtained from roadway cross sections. The lack of availability of this information during PD&E is why FDOT does not commit to noise barrier construction at the PD&E phase. Some aspects, data collection, land use reviews, etc., can occur before 30% plans are prepared, but model input typically does not begin before 30% plans are developed, because those plans may or may not have a firm line or grade typical sections available. If you know pretty generally where that roadway is going to go, you can oftentimes identify where your noise sensitive sites are in order to start identifying your data. You can start gathering some of your data, but typically you don't really get into the nitty gritty until a little bit later on. So the same noise reduction and cost criteria apply in the design phase as was applied in the PD&E phase. This includes the criteria of the noise barrier providing a 5 decibel reduction for at least 2 impacted receptors, and providing a 7 decibel reduction to a benefited receptor to meet the noise reduction design goal. The maximum cost limit of $42,000 per benefited receptor also needs to be met for a noise barrier to be considered cost reasonable. And if the noise reduction and/or cost criteria have changed between the PD&E design, the criteria used during PD&E will oftentimes be used during design to be consistent and uniform. This doesn't always happen. It can be left up to each district, but typically that's what happens. So it should be verified with the district noise specialist prior to applying whatever standards were applied during PD&E, if that has changed. The noise barrier height and length combination that provides the greatest number of impacted receptors a reduction of 5 decibels, as well as meeting the noise reduction design goal while at or below the cost effectiveness criteria, should be the barrier that is recommended and confirmed with the district noise specialist. So we're essentially looking for the largest in length and height barrier that can be built to benefit the largest amount of impacted receptors at a cost reasonable criteria. That's the barrier that we're moving forward with. The barrier that is the cheapest but physically largest, that provides that benefit to the most amount of noise sensitive sites. That's the barrier that we move forward with. So that height and length combination is, of course, confirmed with the district noise specialist. Just because I've run into examples where it's not always the highest and longest barrier that is the best. Sometimes it's, for example, if the 20-foot noise barrier works, maybe it's the 18-foot barrier that actually works a little bit better, based on various physical limitations or project-specific details. So again, that height and length combination is moved forward to an engineering feasibility review prior to initiating any sort of public involvement. And confirmation that the barrier can be built as designed is needed before contacting the public, as it would not be a good practice to contact the public about a noise barrier that is not constructible. So let's talk about the engineering review. The noise barrier engineering review is conducted after a noise barrier is reaffirmed in the design phase to be a reasonable and feasible form of abatement. The engineering review is conducted before any noise barrier specific public involvement, such as surveys or meetings. This ensures that a noise barrier can indeed be constructed as designed and checks for safety, maintenance, right-of-way, utility, and other conflicts. Chapter 18 of the PD&E manual, sections 18.2.3.2.2 through 18.2.3.2.8 outlines the engineering feasibility review factors, including all these safety, access, drainage, etc. These feasibility factors address whether the barrier can be constructed as planned using routine materials and methods, and additional costs solely to accommodate the noise barrier can be included and should be included to the overall cost per benefited receptor calculations. And I want to stress again that the public should not be informed about a barrier if it has not been through an engineering review. So that bottom line there, don't go to the public unless you are 100% certain you can construct it. So this is an example of a noise barrier engineering review form. This form is typically provided by the noise analyst to the engineers, along with a graphic depicting the noise barrier, the stationing extent of the noise barrier, height assumptions, X and Y coordinates of the barrier along the barrier line, a microstation file or open roads, GIS file, Google Earth file, anything that can spatially depict where this barrier will go. So the noise analyst fills out these top rows here with the location. We've got some stationing examples here. Perhaps the barrier is an overlapping right-of-way and shoulder barrier, which we'll get into in a bit here. Perhaps there's an overpass that the barrier has to change from along the right-of-way to along the shoulder of a facility. We've got the lengths here documented, and then we've got the heights. We've also got the estimated cost, and that's pretty much all that the noise analyst can fill in, is just the location, the length, and the height, and what the cost is going to be. And then the noise analyst provides this form to the engineers for them to fill out if there are any design, constructability issues, any drainage, utility, safety, maintenance, right-of-way, any legal issues, outdoor advertising, if it's going to be blocking some legally erected outdoor advertising. And then there's this bottom line of, are any of these issues above severe enough so that the noise barrier cannot be constructed? Oftentimes there are issues that may crop up, but they can be worked around, or there's a solution that still enables the barrier to be built. And then there's some notes on aesthetics, which we'll get into in a little bit more detail later, about what the barrier actually looks like, what colors and textures, if there's any designs, etc. So this engineering review form is typically provided as an appendix to the NSR addendum rather, and that creates that paper trail of if the barrier really can't be built. This gives a paper trail of why it can't be built, so that questions from the public can be answered. So like I've mentioned, Chapter 18 of the PD&E manual does outline that engineering feasibility review factors. They address whether the barrier can be constructed as planned using routine materials and methods. And again, additional costs solely to accommodate that noise barrier should be included in the overall cost per benefited receptor. So the engineering feasibility review is not something that the noise analyst performs themselves, like I mentioned. They put together the form and they fill out those top 4 lines, but they don't know whether or not there are safety and right-of-way maintenance, drainage, excuse me, etc., if there are any other issues. So that's why the noise analyst should consult and coordinate with the engineers in each discipline in order to fill out that form. And that form is, in fact, filled out by each of the engineers in their discipline. So the factors that are considered are safety, access, right-of-way, maintenance, drainage, and utilities, which incorporate overhead and subsurface utilities. So we'll review details about each factor that's considered here. So safety, we've got some height limitations that we have to work with for barriers. So safety factors include reviewing height limitations. It's important to know before designing the barrier so that time is not wasted designing a barrier that cannot be built. Noise barriers must also meet crash test requirements or protected by a traffic safety barrier or guardrail if they are erected inside of the clear zone. This is very important. Additionally, sight distance requirements must be met when the barrier ends approach intersections or cross streets. I have had barriers that needed to be shortened on one end in order to meet safety requirements for getting a clear view for oncoming cars at intersections. And as shown here on this slide, there are various height limitations that go with barriers located at certain locations. So your ground-mounted barriers, so barriers that are located on the ground, not on MSE, not right along the roadway shoulder, those are limited to 22 feet maximum. They're typically located along the right-of-way, which you might hear them be referred to as right-of-way barriers. They're limited to 22 feet due to wind loading and other engineering constraints. There are also crash-tested, cast in place at the shoulder or inside the clear zone. Those are limited to 14 feet. And then barriers that are located along a bridge or wall structures or MSE, those are limited to 8 feet. And again, crash test requirements are required, or crash test barriers are required if they're inside the clear zone there. So this is an example of a barrier that had to be slightly shorter in length in order to accommodate a line of sight for safety factors. We've got this international boulevard here where the barrier likely would have been modeled to be continued a little bit further, but because of safety requirements, we had to shorten that barrier there. So access constraints are also considered in the engineering feasibility review. There are typically not issues on limited access facilities. They occur primarily on non-limited access facilities to accommodate arterials or driveways. Driveways is oftentimes a factor that makes a noise barrier not reasonable and feasible on those non-limited access facilities. The noise barriers cannot block adjacent ingress or egress to properties, of course. Noise barriers also cannot block sidewalks and other normal routes of travel. So this can be avoided by creating openings in the noise barriers to accommodate the driveways and cross streets. However, creating that opening in the noise barrier will greatly diminish the barrier's performance. So if you have to have those openings in order to accommodate driveways or cross streets, typically that barrier is going to not meet the acoustic requirements in order for the barrier to be moved forward. Right of way. So during the review, construction and maintenance of right-of-way needs are assessed. This picture illustrates the supports needed for a cast-in-place noise barrier. Temporary construction easements might be needed if these supports extend outside of the right-of-way. And some districts do not like to entertain the idea of temporary easements. So this is a district by district decision here. So can you build the barrier, and can it be maintained? Maintenance crews must have adequate room on both sides of the noise barrier for maintenance personnel and equipment. Typically, noise barriers are placed 5 feet inside the right-of-way. Of course, this varies by district. Sometimes I've seen 7 feet, so this varies from district to district, but typically it's about 5 feet inside the right-of-way. Some districts prefer noise barriers to be placed right on the right-of-way for arterials so that the noise barriers will not impede future widening. The only way the noise barrier would get built right along the right-of-way, though, is if there's a property owner that grants a permanent maintenance easement. So again, that easement varies by district. For example, District 1, I believe, uses 12 feet inside the right-of-way for a standard location. Other districts might use a different distance, so it varies by district. Drainage factors. So drainage considerations are of importance since the drainage activities occur at or near the right-of-way in the form of swales or other features. Barriers can block drainage if they are not adequately planned and if they don't have drainage features. Those drainage activities should be reviewed in relation to any proposed noise barriers in great detail by the project's drainage engineer for the project. This slide shows an example of drainage features that have been installed on a noise barrier. You see them circled there in red. Louvers are installed to allow drainage to occur, but limits the amount of noise that can come through the drainage features there. Another consideration for drainage is working around a culvert. There are various workarounds to culverts. Perhaps the barrier can be extended with the barrier over top of the culvert, or could the noise barrier post be offset so that the barrier panels would straddle the drainage feature? There's various workarounds to incorporating culverts. Utility conflicts. So utilities should definitely be assessed. They're the most common type of conflict for the noise barrier that is encountered. Utility conflicts can occur both with above ground utilities as well as below ground utilities. If utility relocation costs are incurred by FDOT, they're included in the noise barrier cost effectiveness calculation, and that can be quite expensive. Generally speaking, if the utility is permitted within the FDOT right-of-way and no agreement is in place, the owner of the utility must relocate and accommodate noise barrier at their own cost. That's generally speaking, of course. So this picture shows an example of an overhead utility line over a noise barrier which is being constructed. Potential issues with this include short-term construction equipment clearances, long-term wall clearances, and considering if the utility line can be either relocated or shut down. Many times that power line can be temporarily diverted or rerouted during barrier construction. The only remaining issue after this is then that long-term clearance requirement between the power lines and the top of the noise barrier, which OSHA does have. We'll get into a little bit more detailed later. OSHA does have standard requirements for clearances. So a possible solution is low overhead equipment to drill that post hole. You see these lower equipments that are used with those overhead power lines. If auger cast poles are not available, a spread footing foundation can be used. However, spread footing foundations can be too costly for taller noise barriers due to the size of the footing that's required. This is pictured at the figures here at the bottom. So you've got your spread footing here that is required for barriers that do not have those post holes. So noise barriers can also be side loaded to avoid overhead conflicts. Typically the panels are put in from the top down, which requires a lot of height clearance, but barriers can be side loaded and kind of pivoted in here. So the barrier is the side is put in here to this post and pile panel and then rotated to fit into the other groove here. So potential conflicts are best identified early in the process. Chances that any issues encountered have been encountered in the past on another project. All foreseeable issues must be resolved before proceeding with any design phase public involvement. This is because the resolution of some issues might result in modifications to the noise barrier locations or heights. So you want to make sure you go to the public with the most accurate, up-to-date information about the noise barrier. So let's jump right into public involvement again. So noise barrier specific public involvement does not begin until the engineering review is complete. According to 23 CFR, noise abatement reasonableness requires the viewpoints of property owners and residences of benefited receptors, again, the receptors that get that 5 decibel reduction, to be solicited. Enough responses to document a decision regarding abatement should be obtained. Typically, public viewpoints are solicited in the form of a survey, but they can also be phone calls or solicited during public meetings, etc. Typically, that survey is a written survey that is mailed out via certified mail that they return. 23 CFR states that FDOT can determine the number of responses needed on a noise barrier survey to form the basis of their decision regarding abatement. FDOT has decided that a majority, or in other words, greater than 50% of responders can constitute a decision regarding abatement. So survey methods, like I mentioned, can include workshops, mailed surveys, door-to-door visits, even telephone surveys, etc. Typically, though, it's done in mailed surveys. So this survey, like I mentioned, typically consists of a notification letter and the survey package. So because these are surveys are typically sent via certified mail, a notification letter is oftentimes sent out beforehand so that the property owner is aware that, hey, they're going to be getting a piece of certified mail and it's a survey, please return it. Oftentimes when people get notified that, hey, they've got a certified letter to go pick up or sign for, then they can be fearful that it's a not good thing that they want to receive, like they're being served or something like that. So notifying the public in advance that, hey, you're going to get a certified letter coming is a good thing to do. So that survey package, once that certified letter arrives, it contains a cover letter, it contains a map or aerial showing the proposed barrier location, it's got a noise barrier information sheet about length and height, etc. Sometimes it includes aesthetic options, depending on the district. Sometimes the district likes to be consistent aesthetically throughout their district, so the same texture, the same color, etc. But occasionally the districts will give the option to the community. It's got the survey form, of course, which they filled out, and the addressed stamped return envelope that they can return. And like I said, it's generally sent via certified mail, but not always. Let's see here. So this slide shows an example of a survey letter sent to the public. Really fairly short, to the point. It describes what's going on, what the project is, and how they're eligible for a barrier, and tells them a little bit more information about it and what to do. This is another example of the actual survey. So this is actually an example from Turnpike where they've listed number one question, are you the legal property owner or are you a tenant? And then number two, do you desire the barrier, yes or no? If you're in support, here's a couple of other factoids of information here about access and for temporary access for constructing, etc. They sign their name and they return it. This is an example of some aesthetics for noise barriers. This isn't always, like I said, provided, depends on the district, but there's some pretty good selections here for colors and textures. These are actually provided federally, and FDOT can choose which ones they provide for options here. Homeowners associations, or HOAs. So HOAs may contain common land that is adjacent to the right-of-way, although noise-sensitive receptors may or may not be present. However, homeowners association viewpoints are solicited, but their viewpoints cannot determine the outcome of a noise barrier. So noise barriers are provided to benefit impacted noise-sensitive receptors, in this case, residences. Other types of property owners who own vacant land do not represent noise-sensitive receptors and therefore do not get a formal vote. So homeowners associations can put their input in, but they can't determine the actual output or outcome of a vote for or against a noise barrier. The property owners and or residents can select the color and texture for the noise barrier on the residential side of the noise barrier. Some districts allow for the county or municipality to select the color and texture for the roadway side of the noise barrier, but that's not always the case. And then additionally, a follow-up letter is sent to all surveyed owners and residences to provide the outcome of the survey process. So this table shows the various viewpoint weighting factors, like I said, of residences here, the single family and multifamily, mobile home park, offices and businesses. If they are the owner that occupies the property, they have 100% of the vote. However, if the owner does not occupy the property, the owner of the property has 90% of the vote and 10% of the vote is given to the renter. Of importance, the weighting factor for each unit or mobile home, apartment, condominium is not for the entire mobile home park, apartment complex, or condominium building. So this table is actually provided in Chapter 18 of the PD&E manual, if you want to take a look at it a little bit further. And like I mentioned earlier, that response rate of greater than 50% is desired by FDOT to move that barrier forward. So if a proposed barrier will block the visibility of a legally permitted, conforming and erected outdoor advertising sign, the height of the sign can be increased and the local government or jurisdiction can be notified. However, if increasing the height violates local ordinance or land development codes, the FDOT will inform the impacted and benefited property owners via a written survey. If the majority of impacted property owners vote for a noise barrier construction, the sign height will be allowed to be increased, even if it would be in violation of a local ordinance. Another solution is to allow the sign to be relocated or reconstructed at another location if the sign owner agrees, that is. Additionally, the fair market value of the sign and its associated interest in real property might be paid. That's also another solution. The FDOT must hold a public hearing if that is to occur. If a proposed noise barrier blocks the visibility of a sign, coordination occurs with the FDOT right-of-way office and the outdoor advertisement coordinator. So noise barrier workshops, they can be used to gauge public support or opposition to a proposed abatement measure, including noise barriers. So remember, there are other abatement measures that can be pursued, but typically noise barriers are what is pursued. Noise barrier workshops are also used for informational purposes after a survey package is sent. Surveys may also be completed and submitted at the noise barrier workshops. So typically noise barrier workshops are held separately from project-wide workshops, especially if it is very controversial. So it depends on the level of controversy whether or not a noise barrier workshop, specific noise barrier workshop is held. All right, let's discuss the Noise Study Report Addendum, which is slightly different than the document that is produced for the PD&E phase, the Noise Study Report. So again, the PD&E phase report is called the Noise Study Report, and then the design phase report is called the Noise Study Report Addendum. So the Noise Study Report, or NSRA, should detail the methodology, the results, etc., from the highway traffic noise analysis. It should contain a table of noise level results and aerials depicting the noise sensitive sites. It should have some conclusions, address the construction and vibration, any community coordination, the results of any surveys, the results of the engineering review, etc. An example outline is also found, like I've mentioned, in the FDOT PD&E manual. They've got an example outline for both the PD&E report, the NSR, as well as the design level noise study report addendum, or NSRA. So Chapter 264 of the FDOT Design Manual provides details on noise barrier requirements such as the noise abatement criteria, noise barrier height restrictions, documentation guidance, commitments, public involvement, etc. Other sources of noise barrier design information include the FDOT design standards, the structures design guidelines manual, the AASHTO, the ASHTO specs for structural design of noise barriers, etc. And I believe all those are listed in the resources Word document provided in the handouts section of the GoToMeeting. So once the noise study has been completed, a report is compiled with the results, the NSRA. During the PD&E phase, like I said, that's the NSR. This is now the NSRA, the addendum. The PD&E manual provides those outlines. Those outlines are a guidance. They aren't always exactly stuck to those example outlines. The report should also include a review of the PD&E study, so a brief review of what those results were on the PD&E study. It should include the results of the land use review, the field visit, building permit date and data public knowledge review, a review of the applicable federal and state regulations, and a review of the current roadway design. The design level noise study report addendum fulfills requirements of the PD&E study using final roadway geometry and design level details. So that commitment that the PD&E study made, saying that statement of likelihood saying, yes, we will reevaluate this in the future and the design, and the barrier will be recommended if it's still found to be reasonable and feasible, and engineering review is taken care of and the public wants it. This design level noise study report addendum then fulfills those commitments from the PD&E phase that says that we will do all these things in design. So like I've mentioned, the design level NSRA should also document the engineering feasibility review and include any supporting documentation in an appendix. It's very important to document public involvement activities, especially those related to any proposed noise barriers or abatement. If there's any changes to noise barrier length or heights based on property owner desires, they should be documented in the report as well. Examples of noise barrier survey material should be provided in the appendix of the NSRA, including copies of certified mail receipts. So it's extremely important to document barrier changes based on public comment or noise barrier surveys, as that might be the only, quote, paper trail to these changes. And if questions are asked years later during construction, the NSR addendum will provide the explanation of why it differs, why that noise barrier differs than what was originally found in the noise barrier analysis. All right, time for another live poll break here. So we've got, let's see here, lesson 2, question 2. All right, so back to Mentimeter, and your code is 7823-0293. All right, let's go ahead and get started. So first question here, the noise barrier's height is determined by the engineering feasibility review. True or false? Aha, seems like this was a tricky question, huh? So the noise barrier's height is actually determined by the noise analyst's evaluation of what will work acoustically. However, I can understand a little bit of confusion here. If the engineering feasibility review, let's just say the noise barrier can't go up to a certain height because of some sort of engineering restriction, that could definitely influence the resulting height. However, oftentimes these height restrictions are already on the noise analyst's at the noise analyst's attention, because we cannot design a noise barrier higher than 8 foot on MSE or bridges, higher than 14 feet along shoulders, or higher than 22 feet at the right of way or ground mounted. So I can understand the confusion with this question. But the noise barrier's height is determined by the noise analyst's acoustic analysis results. Next question here, question 2. If utilities are present overhead, a noise barrier cannot be constructed. True or false? False. So if utilities are present overhead, there are various workarounds that may or may not be able to be taken on in order to construct the noise barrier. So just because utilities are overhead does not automatically discount that noise barrier from being constructed. There are various workarounds. So those smaller pieces of equipment, or temporarily relocating or shutting off the utilities, those are examples of some workarounds for a noise barrier to be constructed underneath an overhead utility. Question 3. The engineering feasibility review reviews all of the below factors except acoustic performance. Nice job. So the engineering feasibility review covers access requirements, drainage, maintenance, utilities, right-of-way, safety, all of these factors other than the acoustic performance. The acoustic performance, that is determined by the noise analyst in their highway traffic noise evaluation. So the noise analyst is responsible for the acoustic portion, and then the engineers are responsible for access, drainage, safety, maintenance, utilities, right-of-way, etc. All right, question 4. A homeowner association, or HOA, cannot determine the outcome of a noise barrier survey. True or false? True. So even though that homeowner association might not want a barrier, if all the residences around it want that barrier, they are going to be the one to determine the outcome. Since noise barriers are built for noise sensitive sites like residences, etc., that homeowners association cannot have an influence on the outcome of a noise barrier survey. All right, last question. All engineering issues must be resolved before proceeding with design phase public involvement. True or false? True. So again, the last thing that you want to do is go to the public saying, hey, we have this barrier and it works acoustically and it's going to be great. And the public goes, awesome, we want this barrier. And then if you proceed with the engineering review after telling the public, and maybe there's a safety or maintenance or right-of-way, some sort of issue that completely prevents the barrier from being built, then you're stuck with a situation where you've told the public that they're going to get a barrier, or ask the public if they want a barrier and they say yes, and then they're under the impression that one's going to be built because they said yes, And then you're going to have to turn around and tell them, sorry, we can't build the barrier because we didn't finish fully evaluating that barrier if it could be built. So we don't want to go to the public about a barrier until all issues are resolved, engineering-wise, acoustic-wise, everything. That barrier has to be 100% stamped, signed, sealed, and delivered, can be built, works acoustically, is reasonable, feasible, cost reasonable, everything. Don't go to the public until all of those issues are solved. All right, let's see who won. Very nice. Congratulations, Belle. Nice job. All right, so we are actually at the end of our lesson 2. Feel free to ask any questions in the chat box. We have scheduled a 15-minute break for this time period, but we are running a little bit behind and we took a 5-minute break earlier. So we'll just go ahead and take another 5-minute break here and we'll pick back up on our next lesson, the role of the design team in noise abatement. It is 10:46 right now. We'll come back around 10:51. So we'll have a short break here. I'll put the timer back up on the screen. And we'll see you shortly in 5 minutes. All right. Hopefully everybody's back from their break. We're going to move on to lesson 3, which is a bit shorter than the other ones. So we're going to go over the role of the design team in noise abatement. So this is going to cover the various roles of who is involved in the process. Before we jump in here, I just wanted to make sure we haven't received any questions yet. So I wanted to make sure that you guys have access to the chat window in GoToMeeting. If somebody could just type into the chat window here, yes, we can use it, or something like that, that would give us moderators a little bit of less heartburn that we're not ignoring questions from the audience here. But if somebody could do that, that would be great. And if nobody comments, then we'll find a different way to ask or answer your questions. So lesson 3, the role of the design team. So this lesson is going to present information on the design team roles, including the design manager, the roadway design engineer, structures engineer, utility engineer, geotechnical engineer, drainage engineer, the noise analyst, the district noise specialist, the public involvement specialist, and a few others. You're going to hear the term EOR, which is engineer of record. So that term will be used periodically throughout this lesson here. This lesson is fairly basic and is meant to provide a basic understanding of all the individuals that will be involved in designing noise abatement and what each of their responsibilities are. So essentially, the goal of the design team is to ensure that the wishes of the public and the department regarding noise abatement are met, and that the finished product achieves the intended traffic noise reduction while being constructible, aesthetically pleasing, and can be maintained using standard maintenance practices. And of course, we want that noise barrier to fall within regulation according to federal standards and FDOT standards. So as I mentioned, the design team consists of several roles, which will be covered in more detail in this lesson. We've got the design project manager. It can be an FDOT or consultant, or it could be both. We've got the roadway design engineer, structures engineer, utility engineer, which may include input from utility companies, geotechnical engineer, drainage engineer, the noise analyst or the district noise specialist, and the public involvement specialist. So additional individuals who may be involved in the noise barrier process include district construction engineer, the district maintenance engineer, right-of-way specialist, environmental administrator, landscape architect, the intelligent transportation system or ITS engineer, the lighting engineer, etc. So there's a whole bunch of people that might be involved and roped into this process. So the design project manager, or PM, has the responsibility of managing the project and the team, as well as provide coordination between all of the team members. The PM should ensure that information is available and shared properly. The PM also has the responsibility of coordinating public involvement activities related to noise barriers, such as public hearings or information meetings. The PM should also make sure that an engineering feasibility review has been performed on any proposed noise barrier. So very, very important. The roadway design engineer also has responsibilities associated with noise barriers. They should resolve any utility conflicts, review safety features of noise barriers if needed, and coordinate with the landscape architect, drainage engineer, and the utilities engineer. The roadway design engineer also should prepare the noise barrier control drawings and update the traffic control and utility relocation plans if needed. So let me stress that again, a little hint for our quiz later. The roadway design engineer also should prepare the noise barrier control drawings and update the traffic control and utility relocation plans if needed. structures engineer, in addition to coordination responsibilities, the structures engineer has the responsibility of developing plan notes, required specifications, structural details, and ensuring all commitments made regarding size, location, and aesthetics of the noise barriers are incorporated into the design. Utility engineer. The utility engineer should review wall control plans and roadway cross sections for potential impact on utilities above and below the ground. The utility engineer should also coordinate with the impacted utilities to ensure constructability of a noise barrier and determine utility impacts. This task will typically involve input and coordination with representatives from the respective utility companies that are involved. Geotechnical engineer. In addition to coordination responsibilities, the geotechnical engineer is responsible for obtaining soil borings and reviewing the noise barrier plans for potential impact of soils on the structural design of the noise barrier. So depending on what soil is there, may or may not impact how that noise barrier is built. The drainage engineer. The drainage engineer has the responsibility of providing input regarding the number and location of drainage holes and any drainage accommodations needed in the noise barrier. They also provide grading details and review wall control plans in order to identify potential impacts to drainage structures, drainage patterns, or pond locations. When conflicts occur, the drainage engineer is responsible for suggesting alternatives. The noise analyst, or the district noise specialist. The noise analyst is responsible for assessing noise abatement options in order to provide the design team with any recommended noise barrier dimensions and locations. So remember, the noise analyst determines acoustically and regulatory what will work, and then the engineers determine if there are any conflicts and if the barrier can actually be built. So the noise analyst should provide technical guidance to the design team regarding material option. The noise analyst also reviews any impacts of proposed noise barriers on utilities, safety, maintenance, construction, drainage, right-of-way, etc. So they review the results of that engineering review. If any conflicts arise, they should suggest resolutions and overcome these impacts if possible. So what that means, resolutions, not necessarily what the utilities can do, what maintenance can do, what safety can do, but if for some reason the barrier needs to be shortened for, let's just say, safety, like we saw in that one graphic where the barrier had to be shortened in length in order to accommodate safety, then the noise analyst should make sure that that shortening of the noise barrier would still result in acoustically acceptable noise barrier. So continuing on, the noise analyst also serves as a point of contact for noise-related questions from the design team. Any noise information for public involvement activities and noise barrier survey items are also prepared by the noise analyst. The noise analyst also prepares the noise study report, prepares follow-up information to impacted property owners regarding the status of noise abatement, and coordinates with local officials regarding placement and aesthetics of the noise barriers. Public involvement specialists. So they're responsible for coordinating public involvement meetings as well as providing information regarding noise abatement to inquiring persons. Others that may be involved might be the district consultant engineer regarding constructability issues, the district maintenance engineer for regarding maintenance issues such as access, graffiti, vegetation removal, repainting, etc. The right-of-way specialist, who is responsible for potential easements for construction or maintenance, conflicts with legally permitted outdoor advertising signs, and potential property takings or acquisitions. The district environmental administrator and the district landscape architect may also be involved. The district environmental administrator is responsible for the overall impact of noise on the project area, coordinating with the design project manager regarding go, no-go decisions, reviewing reports and survey information, participating in public involvement activities, meeting with local officials, and overseeing the internal engineering reviews. The landscape architect is responsible for reviewing the impact of proposed noise barriers on existing vegetation, reviewing plans to offer revegetation schemes, assessing noise barrier aesthetics, and coordinating planting drawings. So of importance, you may have seen vegetation exist between roadways and noise sensitive sites. Planting trees is not a form of noise abatement. So we do not consider thick vegetation in between a roadway and a home, for example, a viable means of reducing noise. We can't just go plant a whole bunch of trees or vegetation and go, oh, well, your noise is going to be reduced now. That's not how it works. So another person that might be involved is the District Intelligent Transportation System, or ITS engineer. They will review noise barriers for conflicts with dynamic messaging signs, or DMS, and cameras. They want to make sure that noise barriers don't block the view of the roadway for the cameras, or they don't block the view of those dynamic message signs. The district lighting engineer may also be involved. They will review the noise barriers for conflicts with lighting structures and illumination, as a noise barrier might interfere with illumination and shadows. All right, live poll break. So let's see here. Lesson 3. So we've got a two-parter here, because this is a short lesson. We're actually at the end of our lesson here already. So we're gonna have a two-parter. All right, so menti.com and use code 89145155. All right, let's get started. Remember to answer fast. Which member of the design team develops the structural details of a noise barrier? Structures engineer. Good job, guys. Which member of the design team provides input regarding the number and location of drainage holes and grading details? Drainage engineer. Looks like everybody got that right. That was too easy, huh? All right, question 3. Which member of the design team reviews safety features of the noise barrier? Roadway design engineer. Question 4.
Which member of the design team reviews barrier control plans and roadway cross sections for potential impact on above and below ground utilities? Utility engineer, very good. All right, last question. Well, for this round, which member of the design team obtained soil borings? Geotechnical engineer, nice job. All right, let's see who won. And then we'll do a second round. Awesome job. Nice job, Skids. All right, and on to our part 2 here. Lesson 3, question 2. All right, so enter a different code now. 2554 6861. All right, let's get started. Which member of the design team assesses noise abatement options and evaluate changes? Noise analyst, nice job. Everybody got that one. Easy, easy, huh? Question 2. Which member of the design team coordinates public involvement meetings? Public involvement specialist. Woohoo! Question 3. Which member of the design team evaluates potential conflicts with legally permitted outdoor advertising signs? District right-of-way specialist. That's right. All right, question number 4. Which member of the design team evaluates maintenance issues such as access, graffiti, vegetation removal, and repainting? Maintenance engineer, yes. All right, last question for this lesson. Which member of the design team manages the project? This one's easy. The design project manager, that's right. All right, let's see who won. Nice job, Earthman, very nice. Congratulations. All right, so we are going to head right into lesson 4.
Hey, Christina, this is Doug. I just wanted to mention to the group that we have been receiving questions. We were not aware that they were in the questions box. We were looking in the chat box and did not catch those. So at an opportune time, I can run some of the questions by you if you would like to answer it for the group.
Yeah, do we want to go through a few of them now and then hit our last lesson? Our last lesson is the longest as far as slides go, but I think it'll probably be about a 40-minute presentation. So
yeah, let's bang out a whole bunch of questions real quick.
Okay.
So a couple of people asked if the PowerPoints are available. I assume we'll be able to make these available in some capacity to
Yeah,
folks that are viewing.
Yeah, I would imagine so. The session is also being recorded too, so if anybody has to dip out early, they can certainly get their hands on the recording to watch the rest of the show here.
Okay. We had some questions about the $42,000 per benefited receptor cost reasonableness ratio, how it was obtained and how often that number is updated.
So we actually, FDOT actually reviews that cost information. I believe it's every 5 years, I think it is. We did just review it 2 or 3 years ago, I think it is. So it's coming up in the next couple of years. It's going to be revisited.
Okay.
So that 42,000 was developed off of approximate number of people per household and the average height and length of a noise barrier per household, etc.
It's also worth noting that the $30 per square foot gets updated concurrently with that $42,000 figure. So if construction, if the cost of materials goes up, basically that $42,000 figure goes up. So what that means in essence is that communities that qualify now would qualify in the future as those costs get tweaked over time, but it doesn't really change who would qualify. It's the same over time.
Correct.
I'll throw out one or two more. A question was asked about the design phase. So a reevaluation of noise barriers are required during design for all projects, regardless of whether the design has changed. That was a question posed. So they're asking basically that we still have to do a design phase noise study report addendum.
Yes, in most cases, yes. I have seen it where if a PD&E moves to the design phase and there are no changes, there might just be a memo that happens that says, hey, there's no changes in design, the PD&E level noise study analysis still remains valid. It depends on, it's really project specific, but you're right. In most cases at the design level, a noise analysis is indeed warranted.
Okay. Do you want to continue or do you want to ask some more questions?
Sure, we can knock out a few more.
Okay. I believe this question was posed with regards to when you were talking about site distances and having to shorten a noise barrier in order to have proper site distances. The question was posed, so what happened to the residences that were past the end of the proposed barriers?
I believe in that case, I'm not familiar with that specific project, but I would imagine that those particular residences would not receive a reduction as great as they would have received, because if the noise barrier was shortened, they're not going to get as good of a noise reduction. However, it appears that the noise barrier, even with those residences perhaps not receiving a benefit, that barrier was still reasonable and feasible because enough other residences were able to be provided a benefit so that the wall still remained cost reasonable. It's just kind of the luck of the draw that it happened that the barrier had to be shortened for safety purposes. And I'm not quite sure if there's anything much that can be provided for those residences that, so to speak, got the short end of the stick. Doug, can you think of any other solutions for those residences that
No, we could just simply in the noise study report say there were some, we usually we try to benefit every impacted residence, but that's not always possible to do that. And we do identify locations where noise abatement just simply couldn't be provided for various reasons. In this case, because the wall had to be shortened, but you have other reasons that communities or individual receptors don't qualify under our policy, even if they are impacted, and we identify those.
Yeah. Any other questions you want to go over?
I'll do one or two more here. Somebody asked, what happens if FGT, Florida Gas Transmission, needs to be relocated? Can this cost be taken into consideration for the reasonableness assessment if FDOT has to pay for it, or for any utility that FDOT has to pay to relocate? So relocation costs for utilities that are incurred strictly because we're trying to provide noise abatement.
So typically, if the cost is incurred strictly as a result of noise abatement, and there's no existing agreement in place, then that cost would indeed be incorporated into that cost reasonableness calculation. So you would have the cost of the noise barrier. Let's just say it's $100,000 to build that noise barrier, and it costs $50,000 to move some utilities. Then that $50,000 would be added to the $100,000 for a total of $150,000, and then you divide that number by the number of benefited residences. Although with FGT, it depends on if there's an agreement in place and if they're located inside or out of the right of way, et cetera. I'm not quite sure, Doug, you might be able to enlighten us if there's a different agreement that is in place with FGT with Turnpike as there is with FDOT, but it can be a project by project basis depending on if there's an agreement already in place. Is that right, Doug?
Yeah, in a lot of cases, we have to pay to relocate FGT.
Right.
That's why they're such a contentious thing that Turnpike deals with, because we have FGT throughout much of our right-of-way, and the way the agreement was drafted, we have to take on those costs, not them.
Right.
But in some cases, the utility has an easement on FDOT property, and they may need to move if, for transportation reasons, FDOT is looking to make that improvement. So it boils down to what is the agreement with the utility, and who owns the land and who has the control over incurring those costs. So do you want to do any more, or should we go on to lesson 4? We do have a bunch of other questions.
Let's cover lesson 4 real quick, and then I'm thinking and hoping we'll have 30 minutes left over to cover the rest of the questions. But let's make sure that we can finish the lessons first, and then any questions that we don't have time to answer, we can certainly answer through email, or if we want to hang on the meeting a little bit longer to address whatever questions, I'm happy to stick around and ask.
Very good. Yeah. Sorry everybody that we didn't realize the question. We had some technical issues seeing the questions, so we'll try to answer them.
All right, so lesson 4, designing a noise barrier. We're going to show a lot of different plan sets and various information here in this lesson. So this lesson presents information on the 7-step process of designing a noise barrier, including reviewing the noise study report addendum or request for proposal, designing the noise barrier, selecting the noise barrier types, creating preliminary noise barrier control drawings, locating the noise barrier in the field, determining conflicts, beginning the geotechnical investigation, finalizing those noise barrier control drawings, and then the final review and approval of the noise barrier design. So before a noise barrier can be constructed, a PD&E phase noise study report should document the reasonableness and feasibleness of the noise barrier. Then once the barrier is reevaluated in the design phase, as we've talked about, the structure plans, the noise barrier control drawings, traffic control drawings, roadway plans, specifications, all that is reviewed to ensure the barrier can be built. Once that reassessment is complete and the engineering review has been completed, coordination occurs between the district noise specialist and the noise analyst in order to finalize that noise study report addendum. So documenting the findings of the engineering review, etc. Once all of that process is complete, the noise barrier finally moves into construction. So as I've said, there are 7 steps to this noise barrier design process. We put together a table that outlines each activity that I just went over and who that activity is performed by, because there's lots of different moving parts, lots of different people that are involved with this process. So as you can see, roadway and structures EOR have a lot of that responsibility, coordination with utility and drainage, geotechnical, and the district noise specialist. All of those members are very important in this process. So step 1, reviewing the noise study report addendum, or RFP, request for proposal. So this first step is to review the design phase noise study report addendum. Through this process, the noise barrier location, dimensions, any special notes related to constructability or public input, all of that is identified. Outdoor advertising requirements should also be met before initiating the noise barrier design. The roadway EOR completes this task with coordination from structures EOR. Next, we get to select the noise barrier types. So the results of the noise study report addendum should provide the details of whether a noise barrier is ground mounted or shoulder mounted. The construction type can be determined in this phase as well. In general, very generally, there are 2 types of noise barriers: ground mounted or shoulder mounted. Ground mounted barriers are typically precast, so cast offsite. The panels are made offsite, the posts are made offsite, and erected near the right-of-way, but not always. So remember, within 5 feet or 12 feet of that right-of-way. So, but not always. They can be further in from the right-of-way. Other construction type options include a non-standard precast, a cast in place, or masonry construction on spread footing. If a ground-mounted barrier is located within the clear zone, I've mentioned before, it must be shielded. Shoulder-mounted barriers are typically cast in place and can be located along the shoulder of a roadway, only up to 14 feet. If they're located on a bridge or a structure or along retaining wall or MSE, they cannot be higher than 8 feet. And that's due to wind loading and the requirements for the pilings to be much lower. Note that the MSE, like I've mentioned, mechanically stabilized earth, MSE is considered structure and therefore limited to 8 feet. So this is completed by roadway and structures EOR again. So to design a noise barrier, there are 4 main references to assist with this effort: the FDOT Design Manual, Chapter 264, the FDOT Design Standards, which include the Standard Plans Index for precast noise barriers and cast in place combination traffic railing noise barriers, the standard specifications for road and bridge construction, the FDOT Structures Manual, and the Soils and Foundation Handbook. Of course, this is not an all-inclusive. I'm sure there's many more other resources, but these are the main resources here. Noise barrier length. So the noise barrier length is determined by the noise study evaluation and documented in the noise study report addendum. Now, I've mentioned before, the noise analyst is the person who is in charge of determining the accurate length and height of a barrier to perform acoustically, but that length may or may not need to be shortened based on, like we've seen, safety aspects, utility conflicts, things like that. So in some cases, a taper may be needed to shield oncoming traffic for safety reasons. So for safety reasons, you can't just have a barrier abruptly start right at 14 or 22 or 8 feet. There's a taper that needs to occur for safety reasons for oncoming traffic that needs to be added as well. And that additional length of the taper is actually in addition to the length identified in the NSRA. And a footnote is generally provided, or rather sometimes provided in the NSRA, to make sure that there's no confusion about that noise barrier length that's needed in order to provide that adequate noise abatement. So for example, if a noise barrier is 1,000 feet long, the taper that would be found on the oncoming traffic direction, that taper might be, and I'm just guessing off the top of my head, maybe it's 20 feet long. That 20-foot long taper would be in addition to that 1,000-foot length that is needed for that noise barrier. So the whole length of the noise barrier would be 1,000 feet plus 20 feet. So maximum noise barrier heights, I've mentioned a few times that there are limitations for how high these noise barriers can be constructed. If they're ground mounted, they are limited to 22 feet. If they are inside the clear zone, they have to be shielded for safety and crash purposes. That height restriction is based on wind loading and other engineering factors. If a noise barrier is located on bridge or retaining wall, MSE wall, those are limited to 8 feet. And then if it is a shoulder mounted barrier inside and outside of the clear zone, that is limited to 14 feet. So these maximum heights can be found in the FDOT Design Manual, Chapter 264. A design variation is required when these barriers exceed these heights, although I believe that might be beginning to be phased out, that design variation. So I think that might be on a project by project specific basis. So again, any noise barrier that is inside that clear zone must be either crash tested or shielded by a crash tested device, like a jersey barrier or a guardrail. So it has to be shielded if it's inside the clear zone, if it's a ground mounted barrier. So let's go through some pictures, some fun stuff. So this is an example of a post that is being cast off-site. This is actually an I-beam that is shown in this photo, which is not typical of Florida. Here in Florida, a rebar cage is actually typically used in place of the I-beam. But this is the most common construction method, is precast post and panel. And we're going to go over that in the next couple slides here. So this is a rather old photo of a common construction method of the precast post and panel. So these are some of the panels that are being precast offsite. You can see the rebar that is involved and how large each of these panels are comparatively to the guys standing there. So this picture shows workers drilling a hole for the auger cast pile. Note how huge that crane is that is required for the auger. This is why there are conflicts with overhead utilities most of the time, because you need a lot of that height clearance just to get that auger in to drill the post holes. The post holes are surprisingly deep comparatively to the noise barrier height, which we'll go over later. So in the precast ground-mounted noise barriers, or right-of-way barriers, where they're typically found along that right-of-way, note that the posts are inserted first while under construction. The post is held firmly in place until that grout hardens enough to firm up the foundation of the post. So this is a picture of a post that's being held in place while work is continued on another post or elsewhere. So you see I'll highlight here with my laser pointer. You see that the post is being held in place here while it dries and cures. So here is a picture that shows the typical construction method. So it includes setting the panels in with a crane and assumes no overhead conflicts in this particular picture. If a utility conflict is present, I've mentioned that side-loaded panels can be used, which we'll get into a bit more detail. Once those panels are set in place, grout is added to the post and panel connection to make sure it's firm. So there are several issues that exist with ground-mounted precast noise barriers. It can include leveling of any swales, additional space for cranes, consideration of overhead and subsurface utilities, and traffic control that is required for offloading of posts and panels. So leveling of swales is important so that the panels are level to adequately block traffic noise. You don't want any gaps in that barrier. Maintenance of traffic, or MOT, traffic control is also important at this stage because of the offloading of posts and panels that requires them to be taken off semi-trucks and safely put into staging areas and or moved from the staging areas to their final location. Oftentimes that requires to manage the traffic in that nearest lane at the very least to move those panels and posts to their proper location. So this is a plan. You can see that the precast noise barriers have recessed panels here. I'll highlight that with my laser pointer. So these are the I-beams that, again, are not typical of Florida, but you've got these I-beams here, and you've got the panels that are recessed in just a bit here on either side. On this side here, the panel has been top loaded. So the posts are installed and then that panel is slid in from the top. And then this side here is actually showing an example of a panel that has been side loaded. So putting in one end of the panel and then rotating it in and then making sure that panel is caught within each of those I-beams there. And then those hollow areas are then filled in with a non-shrink grout to make sure that that panel is firm.
Hey, Christina, this is Doug. Just wanted to chime in on that graphic you were just showing, the previous one. I don't think those are I-beams. I think those are just the concrete posts with channels put in them.
Oh, you're right. You're right. Yep. Yeah, the post and pile there. Yep, you're right. Thank you. All right, so designing precast noise barriers. So here is an example of precast noise barrier with some recessed panels and textures on both sides. You can see that that post sticks out a little bit further than the panels there. The graphic on the left illustrates various textures that are available to choose from. Those can be federally provided, and the district has chosen a few different ones to move forward with. So flush panels allow for texture on both sides, but the back side may be limited. So if you see here, you've got the roadway face of the wall that's really flush with the posts. Those panels and the posts are real flush there, so that gives a nice face of the panel that can be decorated. But on the inside here, you've got less of a face that can be decorated with texture or various designs and such. So it allows for texture on both sides, but that back side might be limited a bit. So here's an example of that flush panel. You see how the panels here are flush with the posts, and it allows for a nice uniform look. This is actually the vertical fractured fin texture, both on the panels and the posts. You see how the posts have that same texture there. So nice uniform look. This is an example of the wind loading criteria. This shows, you can see the wind load criteria, the pile lengths and spacing vary based on soil type, post type, height of the wall, etc. So you can see how the spacing of the posts vary. So more specs for standard specifications for noise wall construction here. Section 534-5.1, judgment should be used if any barriers are constructed out of these recommended tolerances. For example, if the panels are engaged correctly and are out of tolerance for the wall, but the wall has no significant aesthetic issues, the wall should still generally be accepted. But the tolerances that are given are pretty tight, but they could be unintentionally, they could unintentionally include walls that are not a problem. So So stick to those thresholds, but use judgment when you're going outside of these thresholds that are listed in the design standards and the standard specs. So the Soils and Foundation Handbook states that borings shall be taken at a maximum interval of 1 boring per 500 feet of wall at a minimum of 2 times the height of the wall, or 30 feet, whichever is less. And Appendix B of the Soils and Foundation Handbook provides the design guidelines for auger cast piles. The normal foundation diameter is about 30 inches, and the general limit foundation depth is about 20 to 30 feet. So that's pretty deep. When I first started learning about noise barrier construction, I knew that those posts went deep, but I didn't realize how deep in relation to the height of the wall. So that was really interesting to learn. The load factors should, of course, be used in accordance with the AASHTO and LRFD bridge design specifications, the load and resistance factor design bridge design specifications. So this picture shows a cast-in-place construction method. Note that the noise barrier uses the spread footing that's here. That's kind of shaped like an upside-down T. So on either side, that noise barrier has that spread footing on either side here. So this picture shows another type of construction method. It's a masonry noise barrier. It involves laying bricks. Shown here is a masonry noise barrier on spread footing. It's not used very frequently anymore, but it is an option. I believe this one here is actually, I think this is the same wall. Maybe it is. I think one part, no, it's this one. I believe this one is in Pinellas County here. So there are a few around, but not very many. Masonry construction can be justified on projects that include barriers with short height, so maximum of 14 feet, in an area where construction access is limited or difficult, where quantities of the barrier, like length and height, is not enough to justify precast noise barriers. For example, maybe the length of the barrier is too short to make a minimum construction material order, or where underground or overhead utilities restrict precast noise barriers. So sometimes masonry is the best option to move forward with. So here's a picture of construction workers erecting a cast-in-place noise barrier along the roadway. Note that the rebar is there, it's set in place, and then they cast it in place along that roadway shoulder. So here's a shoulder barrier mounted along structure. So again, that is limited to 8 feet tall. The barrier traverses over the bridge and the MSE wall here. It's continuous. There's no break in the barrier. There's no change in height, etc. And again, they are limited to 8 feet in height. So here's some examples of noise barriers located on bridges. We've got one that goes over a bridge here, and then one here. You'll note that this is a good example of the opposite end where there is no taper coming off of this barrier because of the oncoming traffic is leaving the barrier. If this was the opposite direction of traffic, if we were looking at the other end of the barrier, it would likely have a taper that comes down to meet the roadway so that it is not a safety hazard here. So here's a plan view of a standard plan of the Standard Plan Index 521-509, which shows a concrete traffic rail with an 8-foot tall noise barrier attached. So the traffic rail is 3 feet here, as you see here, 3 feet. And then the on top, we've got a 5-foot noise barrier for a total of 8 feet tall. The noise barrier is reinforced throughout with rebar, as well as from the noise barrier to the decking. So here's another view of a Standard Plan Index 521-509, which shows a traffic railing with a 14-foot tall noise barrier attached. Note the different types of footing that can be used here. We've got T-shaped spread footing, L-shaped spread footing, or trench footing, just depends. So we've got that 3-foot concrete barrier and then an 11-foot barrier on top for a total of 14 feet. Here's a plan view of a Standard Plan Index 521-512, which is a concrete barrier with an 8-foot tall noise barrier. Got the typical section through junction slab and retaining wall. So one question that comes up over and over again is, why is there an 8-foot restriction on structures, especially the restriction on retaining walls? The noise specialist typically will say that an 8-foot tall wall just won't work. It's not going to provide much of a noise reduction. And the unfortunate reality is that exceeding that 8-foot height, even with a variance, is difficult from a practical standpoint. A few MSE retaining wall mounted wall issues are wind loads. Wind loads on structure are higher than ground mounted walls by code. As the wall gets raised, the wind design pressures get higher. As the load increases, the junction slab size increases. We got to think about what is the anticipated behavior of it as the loads increase. Increased lateral loads on the MSE wall. Even if the overturning factor of safety is met, you got to think about, what about the real probability of failure? Remember the middle third rule of spread footings, the junction slab precast panel interaction, the reflective cracking within the lane limits, the ability to deviate soil reinforcing and junction slab elements. So note that the use of this design concept will require a variance with detailed cost benefit backup. So we stick to 8-foot limitation on MSE and retaining walls for all of those reasons. So see here how the junction slab would need to be extended if it was much taller. So you need a lot more room here in order to make it work. So here's a plan view of a standard index 521-513 traffic rail with a T-shaped spread footing. And a different view of a standard index 521-13 traffic rail with a T-shaped spread footing. This section shows it through spread footing and barrier wall inlet. Note that the noise wall is not shown here for clarity. So here is a plan view of standard index 521-514 concrete and barrier noise wall with an L-shaped footing here. Again, the noise barrier is not shown here. And here is a plan view of standard index 521-515 traffic rail with a trench footing. See how it goes below. As one would expect with a trench footing, the overall depth under the riding surface is much deeper than your L or your T footing. All right, we've got a quick poll here. So let's start up the next poll. So go to menti.com and type in 1676 3771. All right, so question 1. A ground-mounted barrier is limited to what height? So ground-mounted can be all the way at the right-of-way. "22 feet, good job. So a ground-mounted barrier is limited to 22 feet. That can be located all the way out by the right-of-way. Question 2. A noise barrier mounted on a retaining wall or structure or even MSE must be limited to 8 feet. Very nice, guys. Cannot be taller than 8 feet if on MSE, retaining wall, or structure. Question 3. Ground mounted barrier inside the clear zone must be shielded. That's right. So ground mounted barriers can go up to 22 feet, but they have to be shielded if they're inside that clear zone. Question 4 of 5. The noise barrier length may be extended to accommodate a taper. I don't know where that option 3 came from, guys. Sorry. So true or false only? True, yes. So you may have a noise barrier that is 1,000 feet long, and if you need to put a taper on it, that taper would be considered in addition to that noise barrier length. So that noise barrier length can be extended to accommodate that taper. All right, last question. Types of noise barrier construction types include, select all that apply. All right, so all of them. You can have standard precast, you can have masonry wall, you can have a cast in place wall. So all 3 of them were correct. All right, let's see who won. Very nice. Good job, Beyonce. Woohoo! Congratulations. All right, so moving right along here. All right, so special designs, overhead utility conflicts. This picture shows an example of overhead utility line over a noise barrier which is being constructed. Potential issues with this includes short-term construction equipment clearances, long-term wall clearances, considering if the utility line could be either relocated or de-energized or shut down. Many times the power company or the power can be temporarily diverted and rerouted during that barrier construction. So the only remaining issue is then the long-term clearance requirements between the power lines and the top of the noise barrier. OSHA actually provides details on clearance requirements and other safety regulations. So here, OSHA has provided the various clearance distances based on various voltages. So you can see here that the minimum clearance distance of up to 50 volts is 10 feet. You have to have a clearance of 10 feet. And you can find more information about this in OSHA statute 1926.1408. So this picture shows a potential solution to a conflict with the overhead utilities, the low overhead equipment to drill the post holes. I think we showed this picture earlier, where you can use smaller equipment to drill those auger post holes there in order to avoid the overhead utility conflicts. I also mentioned noise barriers can be side loaded to avoid overhead conflicts. So that panel is put in on one side and then it is rotated to fit into both of the gaps there. And then grout is put into the remaining holes to fill the void. It's slid in and made even, and then it's lowered down into place. And that panel is locked into place by injecting the grout right here. That's a non-expanding grout there. So expansion joints are spaced about every 100 linear feet of wall, should include the compressible material or something similar. So spread footing foundations can be too costly for taller noise barriers due to the size of the footing required. Of course, the taller the barrier, the larger that spread footing would need to be. So typically with this option, the spread footing is cast in place and the post can still be precast. This slide shows the typical wind and footing distribution. In addition to the factors of safety against sliding and overturning, the probability of overturning needs to be checked, a stability check using the middle third or middle fourth rule. This check guards against uplift as the edges and softening on the footing toe, so the base there. So making sure that that spread footing is wide enough to support whatever barrier, whatever the height of the barrier is. So on projects with sufficient right-of-way, consider that same spread footing concept as shown in the last slide, only make the MSE partial height with a concrete slope pavement to address maintenance issues related to the slope stability and mowing. So the rigid roadway barrier should be designed for the increased wind loading based on the height above ground. So just some special designs to consider here. So this sketch shows a combination 8-foot retaining wall mounted and a billboard wall constructed outside of the MSE wall volume. Other possibilities include placing the sound barriers inside the MSE volume. Steel casings could be placed in the MSE wall and then posts inserted and concreted after the wall is constructed. But under this option, a 5-foot gutter line offset behind a rigid barrier would have to be provided. This is not without additional costs associated with the cost of steel cans, added right-of-way, added MSE wall fill, etc. And as noted earlier, that we would use actual costs to determine what the cost-benefit analysis of that barrier is. Unfortunately, there's no real magic bullet of how to justify walls greater than 8 feet on structures, as we've gone through. On bridges, walls with greater than 8 foot may involve added beam lines or et cetera to handle the larger wind load and self weights. So districts may decide to provide an additional 8-foot barrier on structures that may be less effective than a 14-foot high barrier, but it's better than no barrier at all. So we've seen this picture before. This slide shows an existing culvert that was accommodated by the noise barrier. We have to think about questions that could it have been possible to extend the culvert or extend the barrier over top of it? Could the barrier straddle the drainage feature, etc.? So just special designs to think about when dealing with culverts. This is another example of a pedestrian bridge overpass where the barrier had to come out and then over in order to accommodate that pedestrian bridge here. In this case, the precast panels were field cut to match the existing tapered pier, and the panels were attached with epoxy bolts and angles, etc. The panels could have been field measured and cast in the precast yard using adjustable headers inside the standard forms, but in this case, they did it in the field. So aesthetics, we've seen this graphic earlier in the presentation. They're also considered when constructing a noise barrier. Various texture options as shown here can be found in the standard plans 534-200. Textures include a smooth texture, ashlar stone, split face, running bond block, fractured granite, wire cut brick, pea gravel, vertical fractured fin, which this is the one that we saw in that the flush panels. The trapezoid vertical fins with fractured face and cut coral block or running bond. So several different options to choose from here. Seen here is an example of the plan table that would include aesthetics for the precast noise barriers. These additions could include graphics or coatings, textures, etc. So this is what would notate the various aesthetics of the barrier. Graphics. So graphics may be developed that are specific to an area. These graphics here were actually developed for a project on US 27 in Polk County that highlights the citrus industry in the area. I've also seen like seashells and ammonites and things like that. So there's various designs that are available to choose from. So this is an example of a single band versus a double band, horizontal band that goes on the noise barriers. You see here, there's just a double band, one here in the middle, one here on top. And then this here is a single band, just one here on the top. So note that if the barrier has any steps in the barrier, so one panel is, let's say, 18 feet and the next panel is 19 feet, those steps would be more pronounced with the dual horizontal band because that middle one would make that step more pronounced. So let's talk about steps. So steps in a barrier should be avoided if there are too many of them. They actually have to be limited to not greater than 1 foot plus or minus 6 inches. So it can be as little as 6 inches of a step, but it can't be greater than 1.5 feet. So one foot with 6 inches. So you have to stay within those steps. You can't increase between two panels. You can't have a difference of 2 feet. So have to stick with that 1 foot plus or minus 6 inches according to the standard plans index here. Drainage holes, we've gone over this a little bit already. They're not to be located, sorry, the drainage holes are to be located as close to the ground line as possible. The need for and location of drainage openings is determined by the drainage engineer for the project, typically during the design phase, part of that engineering feasibility review for the noise barrier. You can see here it shows the drainage features with the louvers, a little bit more of a detail here. Graffiti. So in some areas, this is a concern. So there is such a thing as an anti-graffiti coating. In areas of public access like arterial roadways, you may or may not want to consider this as a feature on the noise barrier. Some areas are of more concern than others, so it's not always applied. All right, so that concludes step 2 of designing the noise barrier. Let's get into step 3, creating preliminary noise barrier control drawings. So the third step here is to create these preliminary control drawings, which identify the limits of the noise barrier. These drawings also show a plan and profile view of the barrier, which depicts the barrier's horizontal and vertical location. So several guidance documents are available to assist with this, including the FDOT design manual, the design standards, structures manual, the soils and foundation handbook. The Roadway EOR completes this task in coordination from structures EOR. Step 4, determining the conflicts. So the fourth step here is to determine conflicts with the noise barrier, which involves a field visit to the location of the proposed noise barrier in order to identify any existing overhead or subsurface utilities or drainage. Any conflicts should be documented. The use of pictures is highly encouraged. Really good to get those pictures and documentation. The Roadway EOR completes this task in coordination with the structures EOR. So step 5 here, beginning that geotechnical investigation. So at maximum, sound wall borings shall be taken at a maximum interval of 1 per 500 feet of wall, or as close to the wall alignment as possible. Extending borings below the bottom of the wall to a depth of twice the wall height, or 30 feet, whichever is less. Boring frequency is increased in areas of suspected weak soils, such as wetlands, filled wetlands, etc. And sound wall borings are required to be performed as the results affect the design of the posts or the foundations because of wind load, etc. And this step is completed by the geotechnical EOR. Step 6, finalizing those noise barrier control drawings. So this involves the plan view, elevation view, and data tables. The plan view shows the noise barrier alignment and location, the beginning and end stations and offsets, including offset definition, step locations, drainage holes, types, and station locations. Those drainage holes, again, are to be located at the ground line. Adjacent overhead or in-ground utilities, limits of sod or and any removal of soil. Of importance, fire hose access holes are actually no longer required. Those could be found on older noise barriers, but those are no longer required. The Roadway EOR completes this task with the coordination from structures EOR. The elevation view of the control drawing should also be finalized, which includes finalizing the beginning and end wall stations, the ground line elevations, top of noise barrier elevations, bottom of noise barrier elevations, post length, drainage holes, including type, adjacent, overhead, and ground utilities, locations and name of noise barrier, graphics, limits of anti-graffiti coating, and this is also completed by the roadway and structures EOR. So section 534 of the FDOT standard specs for road and bridge construction states that shop drawings may be required to be submitted which show a plan and elevation view. So these plans should show the beginning and end wall stations with offsets, the horizontal and vertical alignments of the wall, a lot of the other information that's already been put together for your other drawings here. Panel locations, graphic details, etc., post locations and lengths, elevations, the top and bottom panels, panel joints, etc. A lot of the same information. The shop drawing submittal should also include existing and proposed ground elevations, non-standard precast component details, non-standard post and pile connection details, and lifting devices as well. So these are some examples of some data tables. The control drawings will have tables to inventory the noise barrier requirements for the project. These will include total noise barrier project requirements here, a summary of foundations and wall quantities and limits of anti-graffiti coating. These tables can be found in the FDOT standard plans and instructions index 534-200. Page 10, noise wall data tables. All right, our final step, step 7, review and approval of the noise barrier. So the final step is for the district noise specialist to confirm that the noise barrier design meets the requirements of the recommended noise barriers identified in the NSRA, the Noise Study Report Addendum, and/or RFP. They also ensure that the noise barrier is based on the roadway design concept shown in the final design plans and represents what is being constructed as required by 23 CFR. And this reduces the potential for noise barriers to be improperly designed, so wrong dimensions, etc. So construction of the noise barrier here. A Dear Neighbor letter is typically mailed to notify residences when noise barrier construction will occur near their community and what to expect during that process. So this is typically sent by construction engineering and inspection, CEI, or the project engineer. So this is a picture of how a fence is maintained during the construction of a nearby noise barrier. Note how there's a space between the property owner and the right-of-way barrier here. Here's a picture of a post and panel installation. The posts have already been installed here. Here's a picture of the panels being slid into the posts, which have already been installed. Of note, the overhead power lines here are not as close as they appear. They're not a conflict. These power lines were stacked vertically, so it gives the illusion that they're right overhead, but they're not. Here's more pictures of these panels being slid in. And here, let's see if I can click to start it. This is actually a time-lapse video of these panels being slid in. This was actually a really cool opportunity that I got to go out into the field and witness a barrier being constructed. Really cool to see, something that we've worked on and we've designed actually be constructed. So that was really, really cool to see. You can see how close to traffic they are and how big these panels are and how high they go up in order to place them and slide those guys in. It's really pretty neat to see there. All right, now we've got our last poll break here. So go to menti.com again and type in 73593534. All right, we're gonna get started. Remember, answer fast. When overhead utilities are present, select all that apply. A barrier panel can be side loaded. That is correct. So when overhead utilities are present, barrier panel cannot always be loaded from the top. Barrier cannot be greater than 14 feet. That's not always true because you can have a right-of-way barrier that is 22 feet high. And then a barrier cannot be constructed. There are various methods that we can do to overcome those utilities that are present, including a barrier panel can be side loaded. All right, next question. Graphics are added on all precast noise barrier panels for aesthetics. Every single one of them gets some nice graphics. True or false? False. So not all barriers have graphics. It depends. Question 3. What shows the limits of a noise barrier? Select all that apply. All right, so the limits of a noise barrier can actually be found in all 3 of those options. So noise study report addendum, the noise barrier control drawings, and the shop drawings submittal. All 3 of those should have the limits of a noise barrier. Changes in the height of a noise barrier panel, i.e. steps, so when one panel is 18, one panel is the next height, are limited to what difference in height? One foot plus or minus 6 inches. That's right. So it can vary from 6 inches all the way up to 1.5 feet. Cannot be 2 feet. All right, last question. Make it count. What resources provide information on noise barrier design? Select all that apply. All right, all of these resources. So FDOT Design Manual, Chapter 264, Standard Plans Index, Structures Manual, Soils and Foundation Handbook, all of those actually provide information on noise barrier design. All right, let's see who won. Woohoo! The kid, congratulations. All right. So we have, let's see here, questions, of course, which we'll go over in a second. And please remember to fill out the course evaluation that we have. I believe that I have I think that is it's a handout, I believe is what we did. Is that a handout? Let me see here. Or maybe it's found in, maybe it will be emailed out. Forgive me, I forget what we said that we would do. We also have an exam, which will be emailed out So there's two things I believe that will be emailed out. The course evaluation that's going to tell us how we did, tell us your thoughts on this training, what you liked best, what could be improved, how much you actually got out of these materials, you know, if it was useful for you, any suggestions for improvement, etc. And then we have the exam, which is actually very similar to the questions that we went over in Mentimeter here. So that exam is 3 different sections, anywhere from multiple choice, true, false, matching. I don't think that we have any fill in the blank anymore, but please fill out that exam, and then you can return it to, I believe it says to return it to Terry Cook. So just fill that out and return it to her, and we'll grade it for you and tell you how you did. So fill out that course evaluation and the exam, and I believe now we are on to questions. So if anybody has any questions, please feel free to submit them now, and we're going to go ahead and take a look at all the rest of the questions that we didn't answer earlier in the session here, and we'll go from there. So Doug, if you want to start reading out some of those questions, we can tend to those questions, and if anybody else doesn't have any other questions, you can feel free to sign off. We're not going to go over any more materials. The presentation has been recorded, so if you missed a little bit of it, we'll have that provided for you, or if you know somebody who wasn't able to attend, we can certainly provide this recording to them. And as we've mentioned earlier, I think we can also provide the PowerPoints that have gone along with this presentation as well. So with that, I'll pass it over to Doug to start giving out some questions to be answered.
Okay, so this is referring back to when you were saying that the HOA has no say in the surveys that are performed for opinion. The question was, but what happens when the HOA commonly owned land is where the proposed barrier will be placed? So I think the questioner was thinking that we would put an FDOT noise barrier on the privately owned land.
Gotcha. Well, the barrier wouldn't be constructed on the privately owned land. It would be constructed within that right of way. And if the HOA does not desire or does desire that barrier, the residences within that area actually get that vote. So if the residences want the barrier and the HOA does not, even if there's common area right there, then the residences' opinion would prevail. Now, if there's, for whatever reason, if the common land of the HOA is the only let's say that the HOA owns a swimming pool or some sort of recreational facility that is in itself a noise sensitive area, and the residences of that said HOA are set further back. So let's think of like a golf course or something like that. That's very common to have a golf course be abutted up next to the right of way or the facility, and the residences are further removed back. That would be treated a little bit differently, where if the barrier was constructed and met all the criteria for special land use, like let's look at that golf course again. Let's just say the golf course meets the person hours of use and it's acoustically great, etc. The owner of that particular property would then have the say-so of whether or not they want the barrier. So the owner of that golf course would then be able to say, yes, I do or do not want that barrier. But if it's just the HOA where they're trying to get a say-so in whether or not we can provide a barrier for residences, then unfortunately that HOA does not have a say-so in whether or not those residences get the barrier.
And in that theoretical example you just gave, golf courses pretty much never qualify under the special land use methodology. It's just
correct. Yeah.
There's never enough people using a golf course to qualify. But in theory, if the golf course did qualify, that's
right. Yeah.
the point you're raising. So.
A little spoiler alert, hardly ever do special land uses qualify for barriers. I think I've seen there's probably 3 or 4 special land uses that have qualified for barriers over the years. Would you say, Doug? I can think of 2 or 3 off the top of my head, and I don't recall much more after that. So typically,
we've had a few schools sometimes qualify, but
Yeah, a few schools, recently there was a little middle school that qualified because they had enough of a small playground area that was utilized by enough kids that it was a small barrier with high enough usage that it qualified. So special locations like that do qualify, but for the most part, special land uses, non-residential areas don't qualify. They just don't get the enough usage, so.
okay. Next question, is the outdoor advertising or ODA sign owner responsible for the cost of raising the sign if applicable, if we do identify outdoor advertising impacts as a result of putting up a noise wall?
It depends, and correct me if I'm wrong, Doug, it depends on if it is a legally erected outdoor advertising sign. If it is not illegally, let me state this clearly, if it is not a legally erected noise outdoor advertising sign, then if it's not legally erected, then yes, they would be responsible for the cost of raising that outdoor advertising sign. But if it is legally erected outdoor advertising sign, then I believe FDOT would be responsible. Is that correct, Doug?
I believe so. To be honest, I haven't really dealt with that scenario myself, but I believe you're correct. And I think the term they use is conforming. If it's a conforming billboard,
yeah, correct.
Then that would be the case.
Yes.
Okay, here's a question. Do you have any information on pavement design mix modification to reduce noise as well as speed modification, green grass, trees, etc.? So quiet pavements, basically.
Yeah. So this actually came up very recently. Somebody was, and I forget who it was inquiring about the use of quiet pavement, because years ago it was researched and kind of shoved to the side a little bit, and then it was recently re-brought up whether quiet pavement can be an option, and the same conclusion was come to, that quiet pavement just doesn't really adequately reduce noise the way that a barrier does. I mean, quiet pavement solves the problem of, well, not solves completely, but it helps to address the noise that emanates from the tire pavement interaction, but it doesn't really help too much with engine combustion noise or the exhaust truck stack noises. So quiet pavement has been recently reevaluated, but the same conclusion is it's not a viable abatement measure. And then as far as like grasses and trees and such, FDOT does not consider vegetation as an abatement measure. Vegetation has been proven to not reduce noise nearly as effectively as a barrier. So unfortunately, vegetation is great aesthetically, and it can provide a visual barrier in some cases, which can aid in the kind of I hate to word this like this, but out of sight, out of mind. If you can't see the highway, then you're going to have less of a mental picture that the noise is emanating from it. So vegetation can help to create the perception that there's less noise, but in reality, vegetation has to be really, really dense and several hundred feet thick in order to even put a dent in noise. So, so grasses and ground zones, things like that, quiet pavement, vegetation areas, those are not considered forms of abatement here in Florida.
Okay. We discussed overhead utility conflicts, but how deep does a noise wall typically run underground for it to conflict with buried utilities? I think you kind of mentioned that in your last session here. The posts, or the footings having conflicts with underground utilities.
Correct. Yeah, and I'm actually not an underground utility specialist. I actually don't know how far deep or shallow the deepest or shallowest utilities can be. But as far as posts go for the noise barrier, I mean, they can go as deep as 30 feet. So they can go really pretty deep, and I doubt utilities go that deep, although I could be mistaken. But I don't know what that threshold is for how close, like if utilities are buried at, let's just say 20 feet and a barrier post only goes to 10 feet, is that a conflict or not? I'm actually not quite sure what that threshold is for how close a post can come to a utility. Do you know, Doug, off the top of your head?
Well, let's put it this way, like we deal with FGT, Florida Gas Transmission, quite a bit here at Turnpike. And FGT has what they call their specified width, which is sort of like a no man's land that we have to avoid putting anything at all into that area. And I think it's 15 feet offset from either side of their gas line. So basically it's a 30-foot wide strip that they don't want us getting anywhere, because if they need to do work on their buried gas lines, they need to have the room to either side in order to be able to get their equipment in and do what they have to do. So, laterally, it's rarely a thing where we would be sinking down a post close to an underground utility. Basically, we have a certain buffer offset that we have to stay away from that utility laterally. So the next question, could you clearly explain the difference between build and no build T&M models? Are sound results present for no build present in build sound results?
Aha, so really good question. So in T&M, we have our existing model, so our current roadway, what it looks like right now, what the traffic is right now, etc. And then in order to make the no build future T&M run, what we'll do is we'll simply copy that existing T&M run and then change the traffic. So the only thing that is different between the existing model run and then the future no build run is the additional traffic that comes along with population growth or shipping, trucking, etc. So that is really the only thing that has changed in between the existing model and the no build model. And then for the build model, depending on the project, sometimes we can build upon the existing model. Like for example, if it's a 2-lane going to a 6-lane or something like that, where there's not substantial shifting of the roadway, where they're just perhaps adding in lanes to the outside or the inside of the corridor, where some of those lanes might remain as is, then sometimes we can copy that existing T&M run and then build upon that by adding in the additional lanes or etc. However, I have had plenty of projects where the roadway shifts so much where we just start from scratch, more or less, minus the receptors, of course. If those receptors are largely staying the same and not being acquired, then we might copy over the receptors and the ground zones and the terrain lines, etc., over into our future build run T&M model. But the roadway oftentimes has to be more or less completely remapped out, re-identified all those center lanes, because typically when you get widening projects, you do have some sort of shift of the original lanes that occurs. So just depending on where that shift happens and by how much will determine how much of that roadway you'll have to remap out.
Okay. We got 2 more questions. One is, what is the overall impact that a wet drainage pond adjacent to a noise wall will have? So I assume they're referring to the acoustical effects of that wet pond, basically.
Yeah, that's a great question. So I've run a few test runs in T&M based on if there's a pond or not, and it really depends on lots of different factors, anywhere from elevation to how far away that receptor is that you're trying to ascertain the change at. I certainly wouldn't think that it would influence by 5 to 7 decibels, but I sure have had it influence it by anywhere from, let's say, even just a 1/10 of a decibel, all the way up to, I think I've seen even a 2 decibel difference in noise levels at a certain location based on adding a wet pond versus just a dry pond with a depression. So it really depends, but certainly nothing of large magnitude, but even a 1/10 of a decibel can sometimes be enough to change a receptor from being impacted to not impacted, or vice versa. So
yeah, and we didn't really get into the fundamentals of acoustics as part of this class, but there is, when we code different ground surfaces in T&M. We have what's called a hard site and a soft site. So basically, grass or loose dirt would be kind of a softer surface, whereas asphalt and standing water would be a hard surface, and noise propagates over a longer distance over a harder surface, which is like reflective. If you think about like a stone skipping on a lake versus throwing a stone through a grassy area, kind of the same general principle. So there would be more noise propagated out with a standing water pond as opposed to a softer vegetated grassy surface. And our final question, what's the offsite distance from an intersecting roadway that a noise wall must adhere to in order to conform to safety standards, or is that different per district as well? If so, where might I find that information? So I'm assuming they're referring to site distances with the noise wall when you were talking about having to shorten the wall because of the site distances.
Yeah, that's a great question. I actually don't know the answer to that. That would be found, I imagine, in the standard specs and design standards, all the various resources that we have listed there in the resource page. I imagine that it would be standardized, but I'm actually not quite sure off the top of my head here. Haven't had to deal with shortening a barrier due to safety aspects. Do you know that?
Well, the civil designers would be the ones that would kind of be following the site distance requirements. So that's not typically when we do our engineering review, you know, we would pose the question, are there site distance issues? And if so, you know, how do we remedy that? We're not the best people to answer that question, unfortunately.
So I think we're running out of time here. If you've got any other questions, please feel free to enter them in the questions box here on the GoToMeeting window. Otherwise, feel free to send FDOT an email to OEM. And I also have, so there's, like I mentioned, the course evaluation that'll be emailed out and the exam. If you don't want to fill out a more lengthy course evaluation, I've got another Mentimeter quick poll with 2 questions here that you can just really quickly enter in your free response answers there on Mentimeter. But otherwise, I really appreciate everybody attending. It's been a great session here. I understand that it was a little early at 8 o'clock in the morning, so maybe earlier than some folks are used to getting up. So I appreciate those of you who woke up earlier just to attend. I appreciate the attention, the great questions, and again, feel free to reach out with any questions. We'll be sending out the recording of the presentations as well. And I hope everybody has a great rest of the day.
Bye, everybody.
Bye.